Let's begin our session. First report, Ivan Giorgio, a model to describe the biological stimulus for bone remodeling with a diffusive behavior. Please.
Okay. Good afternoon, everybody. Thanks for your kind introduction. Today I will describe a very simple model to describe the remodeling process which occur in bone tissue. The idea is the following. The bone tissue is not a standard material because it is able to adapt itself to the mechanical environment. In effect, the bone tissue has a function that of weight bearing or protect vital organs. So what we want to model here is the fact that the bone tissue is able to evolve in time and so can adapt itself to the mechanical environment in which the bone tissue operates. So, in order to describe properly this kind of biological process, which is linked with the mechanical activity of the bone tissue, we follow what is the general idea introduced for the first time by Rooks, which is a zoologist, and he thinks to this biological process as a feedback control. So the bone can adapt itself because it changes the microstructure, in particular the trabecular microstructure, or the density of its mass. So what we try to propose is to follow this kind of idea, and the main proposer of this idea was, after Rooks, Frost in the 1987, who's considered for the first time the word mechanostat simply for the analogy of the feedback scheme that we can consider for this biological process with the thermostat which regulate the temperature in a room. So this idea is like follows. We have the bone tissue, which can be loaded with some mechanical forces. And so the bone tissue can change the mechanical properties. I mean, the density, the Young modulus, the other material parameters. How this is possible? This is possible thanks several kind of cells, bone cells, which are inside the bone tissue and act in order to provide this kind of feedback control. The idea is quite simple. We have some kind of cells, in particular the osteocytes, which are able to measure the mechanical state of the bone tissue. So, thanks to this measurement, we know the mechanical state of the bone in a particular instant. Then, this mechanical state is compared with a reference state, and this is quite common in a biological process. So we can estimate which is the difference between the current state with the reference state. And on the basis of this reference signal, other cells in particular, they are called osteoblast and osteoclast, can act directly on the bone tissue. In particular, osteoblasts are cells which are capable of synthesize new bone tissue. Instead, osteoclasts are cells which are capable of resolve bone tissue. So, at the end of the story, simply adding or subtracting tissue, mineralized tissue on the bone tissue, it is possible to change the mechanical properties of this tissue. So, at the end of the story, we want to propose a model which is able to produce this kind of evolution in the mechanical properties of the bone tissue. So, just to clarify the entire process, I want to underline the fact that the mechanical properties of the bone tissue are the results of an optimal, you say, a structural optimal process. Because from one end, you have that the presence of a certain level of mass can be if you have some sources, I mean nutrients, energy, which are able to maintain this level of mass. But of course, if you have a very small level of mass, the strength of the tissue will be very small. So you have a very fragile tissue. So at the end, what we should have is a compromise between the stiffness, which should be as high as possible from a certain point of view, and the presence of mass, which should be as small as possible. So in this, we search for an optimum balance for these two kind of properties. Then we have to underline also that when you add or subtract matter on a tissue like the mineralized bone tissue, we can simply change the density of the tissue. We have to talk about a tissue which is a porous material. So if you add or subtract material, you can change the porosity of this material. So at the end of the story, you change the apparent mass density. But this is not completely true, because if you add or subtract material, you can also change the microstructure. I mean, if you consider inside the bone the presence of trabeculae, they can can be orientated in a particular direction. So if you add or subtract material, can rearrange the orientation of this trabecula. And of course, if you change this microstructure, the material properties of this tissue will change also drastically. Of course, this phenomenon is very complex. So in what we will see now, I consider just the remodeling process related to a change of mass density. So the first step in order to understand what really happened in this kind of evolution problem. Another thing that I want to underline is the fact that the remodeling process happens continuously during all our life. You can imagine that our skeleton is replaced completely 4 times in all our life. And this because every day there is a small part of the bone which is resorbed and new tissue is synthesized in order to maintain the same level of the functionality of the bone tissue. So this can be done for 2 reasons. Of course, during the normal activity, we can have some microcracks, some fracture, and so in order to heal these microcracks, the process of remodeling is perfect because it simply erases all these microcracks, and then a new tissue is added constantly. But this kind of process is also important because of the environmental load that we have. Because if the force that our skeleton should sustain change in time, of course, the mechanical properties of the tissue can adapt. And so we can adjust the mechanical properties of the bone tissue in order to fulfill this function. So what we will do right now is to consider a very simple model. We will talk about the bone tissue in general terms, so we cannot distinguish between trabecular bone, compact bone, and other kind of bone, because we simply want to consider the most simple mechanical model in order to describe this system. And then we simply imagine that if you change the material parameters of this mechanical system, you will have a particular kind of bone tissue. Of course, this is a very complex system, so to start, we will consider an elastic problem. So we don't consider any problem related to plasticity, damage, and other stuff like this. Even though in a more complex model, for sure, we have to consider also this kind of phenomena. And last, I want also to underline the time scales involved in such a phenomenon. The question is quite easy. The remodeling process has at least 2 main time scales. The one related to the mechanical load. You can imagine if you apply a force on a bone, the time characteristic of this force can be of some seconds, some minutes. If you think about a walk, you can have a force with a frequency of some seconds. So, of course, in order to see what happened at this level of time, you have to consider a step in the time of this magnitude. Instead, when we talk about the remodeling process, we have that the entire cycle of resorption and then of adding new tissue is of the order of magnitude of 100 days. So you can imagine that if you want to consider all this time span, the problem becomes easily very complex. So a first approximation that we can do is to consider just one time scale, the time scale of the remodeling, so the slow time scale, the one which is important in few weeks or months. And then we can imagine the mechanical load, which is constant or slowly variable in time. So in a sense, we can neglect what happens if you have a very fast changing in the mechanical force that act on our complex system. From another point of view, we can also imagine that the mechanical force can be regarded simply as in an average way in time. So we see only the effect of averaging on the entire time interval of the remodeling cycle. So in this way, we can simplify drastically the problem, simply considering one time scale. So let's go in greater detail in the model of the biological process. What we use is simply the general idea of a feedback control. We can select a variable, a main variable. In the simplest case possible, this variable can be the mass density. So we can simply imagine to assign the variability of this variable in time. So the derivative of the density with respect to the time. And this evolution rule can be considered as a function of of a certain variable, which can be called stimulus S, which give a current state of the current mechanical state of our tissue. Of course, we can consider this stimulus compared to a reference value of the stimulus. So if there is some change from the current value of the stimulus and the reference one, we have a variation, a change in the mass density. Otherwise, everything remains unchanged, because we have in the right equilibrium for the bone tissue. Of course, we can select also different variables. The mass density is the simplest one, because this is a scalar quantity, you know. We can also decide to consider similar evolution rule described for the Young modulus, for example. So we can imagine to change the stiffness of our material with a very similar, from a formal point of view, from a mathematical point of view, the same expression. Because we can imagine that there is a relationship between the density, the mass density of our system, and some material parameter like the Young modulus. So, of course, it's quite easy to imagine that if we increase the mass density, we have also an increasing of the Young modulus, and vice versa. So, if the mass density change, will change also the Young modulus. And this kind of relation, like this, in which you have an exponential power law of the density, which link the density and Young modulus, can be experimentally evaluated. So we can deal with this kind of relationship. But now let's see in more detail how we can describe this stimulus, which represent the mechanical state of our tissue. Of course, we can refer to the literature, And there are in literature different models to consider the stimulus. And here you can find a list of these models. The first one proposed by Frost itself, you see, 1964, and after that by Cohen, is simply to consider the stimulus as a effective strain. So you can consider the maximum strain or something like that. And so if you reach this effective strain, you will activate the remodeling process, otherwise nothing happens, something like this. Of course, the strain is a tensor quantity, so it's quite difficult to understand how to define this scalar quantity in order to use the stimulus and then the evolution law that we saw before. The simplest idea in this content is to change this effective strain with the deformation energy, because deformation energy represents the mechanical state of our system and is a scalar quantity. So it's quite easy to define and to use in our code. And this idea belonged to Huisges in 1987, which is the most used, employed idea nowadays. But anyway, to be complete, I want also to say you the other models. In 1990, you will find also the paper by Beaupré and Carter, in which they define the stimulus as an effective stress. So the idea here is to consider a certain number of cycles with some amplitude in the stress. So you can act using this number of cycles and amplitude of stress in order to define this kind of effective stress, and so you can define the stimulus in this way. So it's an idea very similar to the strain, but here you use the stress, and you can also imagine to use different kind of cycles with different amplitude and with different frequencies. So it's an evolution of the first idea of Frost. Then, in a similar way, you can also say, if you think about this as a fatigue model, you can imagine to define the stimulus as a quantity related to accumulated damage. So what in the model of Pendergast and Taylor, 1994, they use the accumulated damage to define the stimulus. In a sense, you say, if you reach a certain level of damage, this will trigger the remodeling process. So the osteoblast and the osteoclast, the bone cells, will repair the microcracks that you have inside your model. Finally, it's interesting to consider also the model by Turner, which is a scholar of Frost. And Turner used something very similar to Frost because he used the maximum peak of the strain, but he had another ingredient in this stimulus because other than the strain, he used the frequency of the load. So the idea is this: if you change the frequency in time of your load, you will have a different effect. So if the frequency increases, the remodeling process will increase also. This is the idea of Turner, because there are some experiments that prove that this is a good idea. This kind of example are all defined as local models. Local models of the stimulus, namely, this means that what happens in a certain material particle depends only on this material particle. So you have to evaluate the energy, the effective strain, effective stress, just in this point, and you can evaluate the stimulus in the exact point. Unfortunately, the real object, it's more complicated than this. And the question is this. If you have the real object, the bone tissue, and for some reason you have a part of this tissue which is damaged, in the sense that the osteocytes, the cells related to the sensor part, are died for some disease or for some wound. Of course, inside this region, this particular region, you don't have any signal. So with the local models, you cannot have any evolution in this part. The same if you remove a part of the tissue which is damaged, and you put inside for reconstruct the tissue some graft, some artificial graft, you will see that even though this part, this external part, has no osteocytes, of course, because the osteocytes are the bone cell inside the living tissue, there is some evolution also in this part. So what happened? What is when you put this graft inside your bone tissue? The other cells, the osteoblast and the osteoclast, can go inside the graft. This because, of course, the graft should have some porosity, because otherwise this is not possible. But if the graft is also a porous material, so the osteoclast and osteoblast can go inside the graft, you can see that the evolution can be happen also inside this external graft, or in the necrotic tissue that can be in some case. So this means that you cannot use a local model of the stimulus, because if you do that, you are not able to represent this kind of situation. So you need a stimulus, a model of the stimulus, which is not local, but non-local, in the sense that what happens in a material particle depends not only on what happened in this particular point, but in all a neighborhood of this point. So you are, in a sense, you have to perform some average in a ball all around this point. You cannot consider just the point itself. So, following this idea, in 1995, Whiskys decide to define the stimulus, or if you say here the stimulus minus the reference 1, in this way, where you have a summation. This is a discrete summation. The number is here the number of osteocytes, because the idea is that the osteocytes, which are discrete, acquire this signal, and then what happens in a given point is that the signal is the summation of all these acquisitions. So, of course, you can imagine that here you have your energy for all this point, the point in which you can see the osteocytes. This energy is related to a reference energy, this one. And then you have a weight function which measures the distance between the osteocytes and the the other cells, the osteoblast and osteoclast. So the idea is this: if the distance between these cells is very high, the signal will be very small. If the distance is very small, you will have the highest possible signal. That this is, of course, very reasonable. So if you look at this exponential, you have this capital D, which you can interpret as an influential radius of your osteocytes. And then here, this DI is simply the distance between the osteocytes and the other cells, the osteoblast and the osteoclast, which actually add or remove bone tissue. So you see, this is a very complex model. Then also Wiskes in 1999 proposed another model, which is a little bit different from the previous one. And you see, the only difference is that instead of the deformation energy, it will use the time derivative of the deformation energy. If you remember the model of Turner, there is an aspect related to the frequency. Of course, if you consider the rate of deformation energy, you can take account of this kind of relationship between the stimulus and the time variability of the deformation energy. So this is a quite complete model from this point of view. Of course, you can, in this framework, also introduce some damage variable. So you can also take account of damage, and this is the work by Ambly, 2011, so you see it's quite recent. But at the end of the story, you have exactly the same framework, with the only difference that the Young modulus is not related only to the mass density, but there is also a damage variable. So you can see if there is a damage inside your tissue, and you can act consequently. Finally, we have these two models, which are very similar each other, by Lekszycki, dell'Isola, and by Kumar Yasyuk, in which the previous idea of Wiskes, look, this is a discrete sum of the deformation energy in all the points of the osteocytes with this weight function. Here, in this integral formulation, you have exactly the same idea, but at the limit when you have a density of osteocytes instead of a discrete distribution of them. So you can substitute this discrete sum with an integral, and what is hard, what is difficult to have is that this kind of integral is a convolution integral in the space. So this means that for each point in which you can imagine to add or subtract mass, you have to consider a summation of all the points x0 where you can imagine are present the osteocytes. So you have to do an average of all the information of the osteocyte in your volume. And of course, from a computational point of view, this is quite heavy, even though is more easy to do with respect to this formulation, because this is just a discrete formulation which you have to imagine where the single osteocyte is. Instead, here you can imagine to define this function is a density of osteocytes, so you can put this same expression in a continuous way. The only difference between this formulation, I mean the one of Lekszycki dell'Isola and the one of Kumar-Yasyuk, is the main ingredient used to define the stimulus. I mean, in the first one, you have that the stimulus is an average form of the deformation energy. U is the deformation energy. Instead, in the case of a Yasyuk, you will have this integral, which is none other than the dissipation associated to the fluid flow inside the pores of our porous material. So you can imagine this is a term like the energy dissipated in a Darcy with a Darcy model inside the porous material. You evaluate this integral. You see, this is the power associated to this kind of dissipation. If you perform the integral, you will in the time you will have the energy dissipated. So you can perform this convolution integral to perform this average of the dissipation energy. So the concepts are very similar, but the definition of stimulus is quite different, because here we have the deformation energy and here we have the dissipation. And then here there is also another small difference. You see, this is just a convolution integral, and here you have an average properly said with this weight function. So this is a weight in an average, an integral average of this quantity, quite complex. Now, just to consider this model here, Lekszycki dell'Isola, I want to underline the structure of this convolution integral, because this is the starting point to propose a new model which can define the stimulus in a very similar way to this one. The idea is this. Look, if you consider the stimulus in this way, where you have the deformation energy, this function, which is the weight related to the distance between osteocytes and osteoblast, osteoclast. Here you have the density of osteocytes. This is a convolution. And if you imagine that this function can be represented in this way or this way, you see an exponential in which you have this characteristic length parameter and the distance between the two positions. Look, this kind of expression is very similar to a green function. And you know that this kind of representation can be interpreted as the solution of a partial differential equation. In particular, a partial differential equation of the diffusion equation. So our idea is quite easy. Instead to compute this convolution integral, which from a computational point of view is quite difficult, we can do the following. We define this equation, this partial differential equation. You can easily recognize this as a diffusion equation in which the unknown is the stimulus. And then we have some other terms that now I will describe. But the idea is that this kind of equation have a solution which is very, very similar to the one that we saw before. And you know, it's quite easy to solve this kind of partial differential equation instead to evaluate the convolution of this system. So we define the stimulus in this way as the solution of this diffusion equation. So at the end of the story, we can also interpret this equation and the stimulus itself on this basis. I mean, if this is a diffusion equation, you can interpret the stimulus as an information, a signal, which gives you the information related to the mechanical state of your system. And this stimulus diffuse inside your tissue. So also from a physical point of view, this makes sense. Of course, if you want to describe this kind of phenomenon, you have to define also a source term. And of course, the simplest way to do this is considering a source term which is more or less proportional to the deformation energy in this case. But of course, you can also substitute this with other models, you see the effective strain, the effective stress, or whatever you want. This is not important. What is important is the general framework. And then when this signal is produced and then diffused, of course, the signal cannot be there in the bone tissue forever. So you have also to add some sink term, and the simplest case possible is to consider something which is linear in the stimulus itself. So this means that after...
have 10 minutes.
Okay. So this means that after some time, this stimulus will disappear. So let me say something else about the evolution law that we saw before. Of course, we can so define the evolution of this mass density as a function of the stimulus, and to be also more near to what really happens in this tissue, we can also define a piecewise function in which you have different rates for the resorption and for the synthesis of new bone tissue. Or we can also define some dead zone in which you have the equilibrium instead of just one point. So you can define two thresholds for the stimulus. Inside this threshold, you have equilibrium. And then if you go beyond this threshold, you will have new bone tissue or resorption. Finally, we have to add in this framework of also this kind of weight function. This is a weight function of the porosity, where simply we can say, look, if the porosity is near to 0 or near to 1, nothing happens. So H is like that. If the porosity is near 0.5, there is something which can be happen. The idea is simply this: if you have zero porosity, there is no pores, so the cells cannot activate inside your material. Instead, if you have one porosity, everything is empty, so the cells cannot act because they are not any support on which can operate. So, of course, in the limit case of 0 and 1, you have nothing happens. Something happens only in the middle situation. Finally, the mechanical state. The mechanical model that we use just to do some simulation is a very old problem, a very old model. You can recognize this is the BO model, in which we describe a very simple isotropic material. The idea is this: you have this kind of general behavior, bulk behavior, which is the standard one, isotropic one. Then you have a term which is relating the energy, the deformation energy, which is related to zeta, which is the change of porosity from the current configuration to the reference configuration. So simply the difference between the porosity from the reference to the current. So this means simply that you can store energy when you change the porosity from a mechanical point of view. And then, of course, you need some coupling term between the change of porosity and the trace of the strain tensor. And what is important to say is that here the Young modulus used in this model can change with the density. So if you change the density, also the Young modulus change. So this is the feedback that we talk about this model. So just to finish, let me show some few numerical experiment, in order to see what happens if we do some simple experiment. Let's consider a very simple rectangular tissue. You can block this part and have a tensile test with a uniform load. What happens is this: because of this load, the mass density will change. And here I consider the graph of the normalized mass density, normalized to the maximum value possible, so 1 is the maximum possible here. And this is the time of the evolution in days. And you will see that if you change the amplitude of the force, the evolution of just one point, but you know the density is uniform, so every point have the same evolution, because everything is uniform. You see here that if the force is of this on a certain level, you have no any change. Everything remains constant. So you have in the reference state. But if you increase the level of the force, you will have this asymptotic behavior. You will have a production of tissue. And of course, if you continue to increase the force, you will have a greater density. On the other hand, if you decrease the value of the force, you will have a resorption. So the mass density will decrease. And the less is the amplitude of the force, the less will be the density of your system. Then let's see also this other simple case. If you have a healthy area of the bone and a necrotic tissue, necrotic means there is no osteocytes, so here there is no signal at the beginning, and you perform the same behavior. Now there is some change in time with respect to before, and this is the plot of the mass density. You see at the beginning everything is with a normalized mass density 0.5. But this is the necrotic zone. So if you apply a load, you will have an increase of density in the healthy area, but nothing happens in the other necrotic zone. If you continue to apply the load, you will see that the new bone from the healthy zone to the necrotic area will appear for this non-locality of your model. And then, finally, if you go to the end, you will see that the mass density is changed. This is 0.5. This is 0.84. So you will have that here there is, in the necrotic zone, also new bone. So there is an healing process. Finally, the very last example I want to show you is what happens if you have some load which is not uniform. So you have a stimulus which is not uniform. You know, if you consider this kind of load, here you have a sort of neutral axis, so the stimulus is low here. And in fact, if you see some evolutionary time, for the mass density, you will have that in the central zone where the load is zero, you have this kind of behavior with a less mass density produced, and near the border where the load is great, you will have a greater production of bond density. So you will see that it's simply by tuning the material properties of our system, we can describe, at least in this very simple case, from a qualitative point of view, what happened to the bone tissue as an evolutionary system. I mean, here just a few reference in order to see the principal work about this kind of stuff. The first work by Frost, I mentioned before, and the Mühlender-Riskes. The important work of Lekszycki dell'Isola about the convolution. And the last one is about this kind of model with the diffusion. And for me, that's all. Thanks for your attention.
Thank you for your report. Have you got any questions?
Yes?
Thank you for your interesting report.
Mm-hmm.
I have a small question. Are you planning to try to take into account maybe some basic peculiarities of the microstructure of
Yes.
maybe, for example, I had the idea, if, for example, you consider the bone as the bone pierced with the tubules, you can try to model the dentin, because the remodeling of dentin is on the frontier of the clinical
Yeah, I see.
dental science.
Okay, look, you know, as I tried to explain before, this model is quite complex. So we start with a very, very simple case. You see, for a mechanical point of view, I just consider an isotropic material, which is the simplest one I can consider, with the only microstructure related to the porosity. So you change the density and you obtain some different behavior, okay? Of course, in general, you have to think about some orthotropic material, especially if you consider trabecular systems. And you know, when you consider a orthotropic material, you have to deal with many material parameters, not just with two as in the isotropic case. So this is what we plan to do in the future, but for the moment we simply consider this very, very simple mechanical problem, just to understand the biological part. Because, you know, the important stuff for us is to understand how interact the biological part with the mechanical one. Then when we understand completely this part of the model, we can consider mechanical problems much more complex. But you see, we always go step by step, one single step by the other. So we don't do anything about other kind of microstructure. The only microstructure that I consider is the porosity, and that's all.
Thank you once more.
Okay, I can stop.
Good afternoon, ladies and gentlemen. My name is Andrei Vasiliev, and I would like to speak about our try to model nanoindentation experiment. And our idea was to construct the simplest possible analytical model, which can be used for analysis of nanoindentation in terms of determining elastic properties. First of all, I would like to say a few words about what nanoindentation is. It is a set of experimental methods which gives you a possibility to apply local load and simultaneously record the deformation response from the material. Usually, the load is applied, not usually, the load is applied to the material through the special instruments which are called indenters, and the most commonly used are the spheroconical one and pyramidal indenter, which are illustrated here. The result of nanoindentation experiment is, you can see here, is the load displacement curves. And if we speak about the determination of elastic properties, then the unloading curve is interested, and namely the most commonly used Oliver-Farr method is as follows. We analyze the unloading curve and try to obtain the derivative of the indentation force with respect to the depth. This data give us the information about the elastic response. And the idea of the Oliver-Farr method based on this, but the mathematical model which it based on deals with the homogeneous bulk materials, and it is the simple case, and here is the formula to obtain the Young's modulus, which they called reduced modulus. They use this expression, and as I said, the main quantity is the indentation stiffness, which is this. So the problem is this technique is good for bulk materials, for coated materials, but when the coating thickness is big. But if we speak about thin coating, for example, when the thickness is close to 300 or 500 of nanometers, then it can be a problem to obtain elastic properties of coating because we have not only the coating response but also a substrate response, and the literature suggests us to make experiments on depth not exceeding 10% of the coating thickness, which is not always can be done, because if the thickness is small, then such a depth can be comparable with the asperity height and roughness and something else then we have a wrong result. So the motivation of my talk is that we need to obtain new models if we want to analyze nanoindentation of coated materials. Another important issue is that if we speak about not even thin coatings, but if the elastic properties of coating and substrate have a big difference, then it also can be a problem. Okay, so speaking mathematically, nanoindentation can be described as a contact problem, and we consider following contact problems. They are similar to the classical ones. The main difference is that the material, the Hall space, consists of two parts: the homogeneous substrate with the elastic properties being constant, and a coating of thickness h, the properties in general be the function of depth coordinate. So we can model not only homogeneous coatings, but also functionally graded multi-layered coatings too. The statement of the problem you can see on the slide. It is just in the classical contact mechanics. And it is also well known that such a problem can be reduced to solution of singular integral equation. The main difference is that the kernel transform of the integral equation for homogeneous material, it would be unit, but if we speak of for chaotic material, it is some function. And for it can be obtained analytically only for some particular cases. For example, if the coating is homogeneous, or if we consider functional graded materials, but with specific variation in depth, for example, exponential or linear. In general case, this function can be obtained only numerically. The idea of our model is that we would like to approximate this function by such an expressions, which makes us opportunity to solve this integral equation analytically. And here you can see the solution for two types of geometry of indenters, for spherical one and for conical one. And it is important that the solution can be described by two terms. First term describe just the solution of Hersham problem, the homogeneous bulk materials with no coating, and the second term is an additional part which comes from the coated substrate system. The same situation for the conical punch. And it means that we have the same singularities as in classical cases. For conical punch, we have logarithmic singularity at the center of the contact, and so on. If we speak about nanoindentation, then we need to have expressions for indentation force, indentation depth, and indentation stiffness as function of contact radius, and they are presented on this slide. And once again, they can be, we have a part which correspond to the homogeneous material without any coating, and we have some additional part which describe the coating response. And it is important that this part depends on two dimensionless parameters. First one is parameter lambda, which is geometrical parameter, and it is a relation thickness of the coating. It is a ratio of the coating thickness to the radius of the contact area. And we have multiple parameters AI, which describe they are the parameters of approximation of the Kernel transform. They depend on the ratio of elastic moduli, effective moduli of the coating and substrate. These are the same expression for spherical punch. Okay, so the next step is the problem is that we have multiple parameters related to our approximation, and it is not very suitable for analysis of experiments because we need to have some correlation between them and between the elastic modulus which we want to obtain. So we try to simplify it as possible, our model, and we consider the case, the simplest possible case. Then our approximation have only one parameter. And this parameter, this case give us a possibility to obtain simple expressions. They are implicit expressions for all required quantities such as indentation, force, depth, and indentation stiffness as well. They depend only on one parameter A, and it can be easily related to the relative Young modulus of the coating. On this slide, I try to illustrate the dependence. For one example of homogeneous coating, I illustrate how this unphysical parameter A of our model coincides with the parameter B, which is the ratio of effective modulus of the substrate and the coating. And the lowest figure is the relative error of approximation. The main thing that we can see here is that the error of approximation depends on the ratio of elastic properties, and the bigger ratio is, the higher error we have. But for metal or ceramic coatings, this ratio is about 1/5, 1/2. So for these cases, we are interested only in this region, and the accuracy of the approximation are quite satisfying. And it is important that the accuracy of this approximation, the accuracy of the result of the solution of the contact problem is the same order of magnitude or even less than this quantity. That's why it is important to realize this error. Okay, next step, I would like to provide some numerical results. To simplify this, I would like to speak only for the case when the coating and the substrate have equal Poisson ratio, but the Young modulus are different. We consider 6 homogeneous coating with following values of parameter beta, and it means that elastic modulus of coating and substrate differs in 10 times, 5 times, and 2 times. And we consider also 4 types of functionally graded coatings with linear and exponential variation as the more general ones. Okay, in this slide, you can see the graphs of kernel transforms, and they are important mostly for us because, as you can see further, they have in common, they have a lot of similar behavior. They have similar behavior as the graphs of more practical quantities like indentation stiffness. This slide is about the accuracy of the simplified approximation and not simplified, when we can use as much parameters as we need to. So you can see that, as I said before, that the accuracy of the approximation highly depends on the parameter beta. And we have, so you can see the values. I would not speak more on this. Okay, the next 3 slides will be about the analysis of accuracy of results. We compare the results for simplified expression with the results of the best approximation we can construct. The first slide is about the radius of the contact area, and here and further solid lines would be the most accurate approximation, while dot lines is the simplified solution. The main results are presented in the table here, and you can see that the maximum error is about 7% for the most bad cases. If we speak about the ratio of the young modulus 2 or 5 times, then the accuracy is about 1 to 3%, 4% here. And the biggest error is observed in the intermediate coating for coating of intermediate thickness. It is important also because the most practical, the most important for practice are thin coatings, and for them the accuracy is better in our model. Okay, the same situation for indentation depth and indentation stiffness. Similar numbers are observed here. And a few words about the contact stresses. The solution of the contact problem are the contact stresses on the surface. And knowing them, we can establish all strength state of whole material. That's why they are so important for us. If we speak about the conical punch, then it is also well known that we have a singularity at the center zone of the contact. And on this slide, I illustrate this function, which is the relative distribution of the contact stress. So I put the singularity out of this function and analyze the ratio of the distribution of the contact stresses for coating materials to non-coating one. So it lead us a possibility, give us a possibility to compare what is happening when we add a coating, and similar to the correct theory, it is important quantity what is going on the singularity coefficient, so the contact stress distribution near the central zone. And it is seen that if we speak about thick coatings, green lines here and here, then this distribution is rather constant. So it means that the presence of the coating have no significant effect on the contact stresses. But if we speak about thin coatings, then we have a big difference, especially near the central zone and near the edge of the contact area. We have such high rate of distribution. I don't know how to say it exactly. So we see some gaps near these points. And moreover, because we have analytical results, we obtain these coefficients analytically, and they have quite interesting structure. It was obtained that they depend only on this dimensionless parameter beta. Okay, this slide illustrate the accuracy of the simplified model in means of contact stresses. On vertical ace, it is coordinate R. On horizontal axis, it is relative coating thickness in logarithmic scale, while the color is the relative errors. Upper figure, it is the case of homogeneous coating with parameter B equals to 0.5, while the lower one, B equal to 0.1. This is the one of the most good example for us, and this is one of the baddest one. And we can see here that for the upper case, the accuracy are rather good for any type of parameters, while for the lower figure, we can see that the accuracy can be big. It means that we need to be careful with this simplified expression, but it also should be pointed out that the region where such a big accuracy is observed is rather narrow. So if we speak about the coating of intermediate thickness, then these simplified expressions are not very effective. But if we speak about thin coatings, this region or thick coatings, then our models are quite effective. Our simplified models are quite effective. And the last part of my presentation is about the comparison between the model and between the experiment. So we consider two specimens, the similar coating material, zirconium nitride, and different substrate. First one is copper, and second one is silicon substrate. We make a series of nanoindentation experiments and try to establish the correlation between our result, theoretical result, and experimental result. To obtain the elastic properties of this specimen, we did some experiment for the substrate before the deposition of the coatings, and here are the example. The Poisson's ratio we get from the literature, and the elastic properties of zirconium nitrides also we got from the literature, and also we established them by experimentally too. Okay, here are some data about the deposition of coatings. I would not speak about them. If somebody would be interested, then I will show them later. We analyze the roughness of the surface. It is important because we need to be sure that we have rather flat surfaces. Otherwise, the result of the experiment would be not fair. We see that the surface have some big asperities, but we can make positioning of the indentation tip and make sure that our experiment not contact with such a big asperities. For silicon substrate, the surface is rather flat. I think it was connected with the roughness of the substrate we use. Then the second step, we estimate the thickness of the coatings. For that purpose, we use ion beam etching and then scanning electron microscopy to obtain the thickness of both coating that we used. Okay, and then we make a series of nanoindentation experiments. Here you can see the regions of indentation force and indentation depth in these experiments. And the last results are the comparison between the experimental data and theoretical ones. Red line are the experimental data, while black dotted line is a theory. On this slide, we illustrate the comparison for copper substrate, and it can be seen that up to the indentation force equal to 70, we have a very good agreement, but after that, the results are quite different. It can be explained by the following. Here you can see the load indentation curves, and it can be seen that up to when the load increase in some critical point, which is equal to 70 nanonewtons, micronewtons, then we see a step on this curve. It means that something inelastic happens. That's why our model can be effectively used here, or we need some kind of changes in the model. For silicon substrate, we have a very good agreement for almost any region of indentation force we observe. And it is a good news for us. And so I think it is the end of my presentation, and in the end I would like to once again speak about the general idea of our work, and it is only the first step in this work. We just create a model, we compare it to the experiment, we analyze the accuracy of our model, but the next and the most important step would be to use it in practical aims to obtaining the young modulus of real materials. So thank you very much. This is the end. I would like to answer any question. Do you think that you may take into account the peculiarities of the Berkovich indenter in the future in your model, because it has sharp edges and so on? Yeah, thank you for the question. Actually, the idea that we use is similar as it is used generally in analysis of experiments by Berkovich indenter, and it is the software which is used for that purpose also use the same idea. The idea is that nevertheless the indenter is sharp, but the main thing is we need to know the contact region. We need to use in the model the same indenter which give us the same region of contact. This is the main thing. It is not very important that it has sharp edges because we analyze the unloading curve. All inelastic response is observed in the loading curve, while the unloading is pure elasticity.
You look sometimes conical indentation. It is possible to use conical indentation to determination of the properties of coating. When it possible? Condition, which one?
Actually, when we speak about the spherical indenter, we have to understand that it is spheroconical one. So conical geometry is natural for the indenters that used in practice. So it's the first. Secondly, which I just told to previous question, is that the most important thing is the same contact region that we use in model and in reality. So the geometry, the real geometry, is it a pyramid or is it a conical one? It is not very important, and in practice, it's not our idea. It is used right now. Then, huh? Yes.
Я бы спросил, конечно, если возможно. Это возможно или нет?
Yes, please. I am listening.
Can I say? Can I ask?
Yes, yes.
Yes, thank you very much. I would like ask a short question. Sorry me, I late. What is your mind? What do you understand under effective modulus for body with coatings? Can you say that shortly?
Effective modulus, we distinguish the effective modulus of the coating and effective modulus of the substrate. But the effective modulus is the same as in classic. It is the ratio of Young modulus to 1 minus square Poisson ratio square.
So is it modulus for substrate or coatings? Can we divide this one or not? Only substrate?
No, we analyze the ratio of effective parameter B in our model. Here.
Yes.
is the ratio of effective modulus of the coating to the substrate, and we want to establish.
Yes, thank you. I understand this one. Can you divide after experiments models for coatings and substrate or not?
Yes, we want to obtain one of them. We need to know, for example, effective modulus of substrate, and we want to obtain effective modulus of the
coating. Okay, thank you.
Any more questions? Thank you once more. Людмила Венатовская готова, да? Вот давайте посмотрим у нас доклад. Вы following.
Hello, dear colleagues. I'm glad to see you all today. Do you hear me? Can you hear? Yes, okay. The theme of our research is evaluation of biomechanical characteristics of the eye after surgical hyperopia correction. I'll be the keynote speaker today. And I want to say that this work was proposed by ophthalmologists of the Cheboksary branch, Fedorov National Medical Research Center, MNTK Eye Microsurgery. In the present paper, we consider the method of elastotonometry to assess changes in the biomechanical properties of the cornea after LASIK and femto-LASIK correction of hyperopia, in other words, farsightedness. In recent studies, a change of elastic properties of fibrous tuning of the eye in clinic and treatment of many eye diseases, including myopia, it means nearsightedness, and glaucoma, is widely discussed. It is known that its non-mechanical properties vary significantly in both myopia and glaucoma, and those changes are multidirectional. In both cases, scleral stretching occurs, but in myopia, the strength properties of the sclera decrease, while in glaucoma, those properties increase. Ocular response analyzer, ORA, can only state the presence of biomechanical disorders of the fibrous tunic, fixing the same decrease in such parameters as corneal hysteresis and increase in corneal resistance factor in myopia and glaucoma, and doesn't differentiate the different nature. The results of current research have shown high sensitivity of the elastotonometry to the presence and type of biomechanical disorders of the fibrous tunic of the eye. This method was proposed by Filatov and Kalfa and was originally used only for the diagnostics of glaucoma. And the method is based on consecutive measurements of intraocular pressure by McCluskey tonometers. You can see them here. It's a plummet weighing 5, 7.5, 10, and 15 grams. Then the dependence curve of tonometric intraocular pressure versus tonometer weight is plotted. The nature of curve, which is called elastic curve, makes it possible to analyze the biomechanical state of the outer shell of the eye. When here you can see elastic curve for the normal eye and the elastic curve for the eye with glaucoma. When analyzing the curve, its beginning, range, shape, and the rise are taken into account. It is known that deviation of the elastic curve from the nose occurs in such corneal diseases as glaucoma, marginal ectatic dystrophy, when the non-uniform cornea becomes particularly weak in the vicinity of the sclera. The surgical correction of hyperopia also leads to the weakening of the cornea at the periphery. Nevertheless, the behavior of the particles haven't been studied enough. It is known that modern tonometers are very sensitive to the thickness of the cornea, and measurements obtained by Malysheva tonometer, which was proposed back in 1884, still remain the most accurate. In this regard, after surgery on vision correction, which changed the curvature and thickness of the cornea, applanation Malysheva tonometer is used. In the Malysheva method of measuring of the intraocular pressure, the tonometer with the flat foundation is placed on the cornea. Under this, lowered cornea deforms, and the diameter of the imprint created by the contact with the instrument is measured. Here you can see other types of tonometers, for example, Goldman's tonometer, which is assumed to be the gold standard of tonometry in USA and all other countries. IKEA tonometers, Perkins tonometers, Schultz tonometers, but they are too sensitive to the readings obtained after surgical correction of different eye diseases. LASIK, Operation LASIK, surgery LASIK is currently considered to be one of the most effective methods for correction of various refractive errors. LASIK surgery consists of creation of an anterior corneal flap, biomechanical microkeratomy with the following laser ablation. Laser ablation means vaporizing of cornea material by laser. In hyperopia correction, the stromal tissue is removed in an annular mid-peripheral region of the cornea in this region. This leads to difficulties in creating flaps with sufficient diameter so that an appropriate ablation could be performed. In the last decade, a new form of refractive surgery was proposed, which includes femto-LASIK. So you can see the similar name, but another type of laser is used. Femto-LASIK. Femtosecond laser forms an ideal circular interface consisting of tiny cavitation bubbles in the cornea. Thus, it can create cornea flaps of various shapes with precise diameters and depth. You can see this flap here. Flaps in LASIK are not uniform in their thickness. It is known that the cornea has a complex biomechanical structure and consists of 5 main layers of different thickness and different biomechanical properties. The stroma is the thickest layer of the cornea. It is placed between 2 thin but strong membranes, Bowman's membrane and the cement membrane. Corneal stroma is composed of flattened lamellae, layers of collagen fibril, and experimental studies indicate that the material on the cornea as well as material on the sclera is highly anisotropic and heterogeneous. Here you can see our finite element model. The corneoscleral eye shell is modeled as joint spherical segments with different radii and different elastic properties. This spherical segment represents cornea, this sclera. It is assumed that before loading, the composite shell is filled by incompressible liquid with true pressure P. Therefore, the problem of the stressed state of the soft and close to soft shells under the load with a flat base tonometer is solved numerically by selecting such tonometric pressure at which the application of the load doesn't change the internal volume before loading. You can see here that we split cornea into 4 layers, and here you can see the part of cornea that is removed during the surgery. The present finite element simulation, in our simulation, the intraocular pressure is defined as it used in applanation tonometry by the following relation, where W is the weight of the tonometer, S is the contact area. In the simulation, the intraocular pressure increases due to cornea loading with tonometer, and it is assumed that internal volume remains constant. By this means, the intraocular pressure is obtained. Increased intraocular pressure is obtained. Nonlinear analysis is performed by means of software ANSYS. Axisymmetric large deformations are considered. According to clinical data, it is assumed that during LASIK correction, an angular layer of the cornea tissue is removed with a laser beam. It's shown by yellow. During femtolase correction, an angular layer of the same width but with greater inner diameter is removed. Here you can see our parameters of the surgery. They are corneal flap thickness, ablation zone width and depth, and some parameters of the ablation zone. Outer diameter for 2 types of surgeries, femtolasic and LASIK, and internal diameter for LASIK and femtolasic operations, surgeries. We assume that elastic coefficients of the cornea and sclera are close to transversally isotropic materials. Here you can see parameters of the main layers of the cornea, the thickness of each layer and its elastic moduli, sclera parameters, and ablation zone parameters. In this slide, the further results will be presented for the following surgery parameters. We assume that in femtolasic surgery, the thickness of the flap equals to 110 microns. In LASIK, the flap equals to 160 microns. The ablation zone width and depth are fixed. Numerical calculations show that after refractive surgery, the band stiffness of the cornea reduces and consequently reduces the intraocular pressure readings obtained by applanation tonometers. It was found that intraocular pressure readings depend on the inner and outer diameters of the angular layer, on the depth of the ablation zone, and on the thickness of corneal flap. The changes of the intraocular pressure readings obtained by Maklakov tonometers were imperceptible. Under LASIK surgery, the angular layer with smaller inner and outer diameters is removed, and thicker corneal flap is cut. Thus, larger deformations and displacements in the thinning region, here you can see it, is observed. Here you can see the profile of the inner surface of the cornea before the surgery and after the surgery. Here, displacements are shown. Here you can see the results for intraocular pressure, 15 millimeters of mercury. Here, intraocular pressure equals to 25 millimeters of mercury. In this slide, the contact stress distribution is presented for the Maklakov tonometer, weighing 5 grams. These results before hyperopia correction after LASIK and after femtolasic. On this slide, the results are presented for the tonometer weighting 7.5 grams. When we obtain 10 grams, we see that sclera takes influences the results obtained by tonometers. And the last slide, the results for the Maklakov tonometer weighting 15 grams. Here you can see elastic curves, which are made for intraocular pressure 15 millimeters of mercury and 25 millimeters of mercury. When analyzing the curve, we analyze its beginning, range, shape, and the rise. The rise means the difference in the readings of the tonometers of larger and small weights. The rise indicator, according to Kalfa, can serve a measure of elasticity of the eye. In normal eye, the value of intraocular pressure at the beginning of the curve doesn't exceed 21 millimeters of mercury. Its range is between 7 and 12 millimeters of mercury. The average value is 9.9, and the maximum value doesn't exceed 30 millimeters of mercury. The results of numerical simulation show that after surgical correction of hyperopia, flexural rigidity of the cornea reduces, therefore the rise of the elastic curves increase. For the elevated intraocular pressure, in our case 25 millimeters of mercury, the stronger rise of the curve is observed. After LASIK surgery, the rise of the curve increases considerably due to elevation of the true intraocular pressure, while in preoperative state and after femtoLASIK, this change is not significant. For the last two cases, for femtoLASIK and before surgery, the dependencies on the intraocular pressure readings obtained by Maklakov method on tonometers is almost linear. This may be explained in such a way that after LASIK surgery, the larger deformations and displacements in the ciliary region of the cornea are observed, which indicate the greater decrease in flexural rigidity of the cornea. When also we made such conclusion that when tonometer overlaps the ablation zone, after LASIK it occurs at load 10 grams, after femtoLASIK at a load close to 15 grams, the contact area begins to grow rapidly and tonometric pressure starts to decrease. As a result, the LASIK curve becomes broken. The last data obtained in Cheboksary branch of Fedorov I Microsurgery Federal State Institution also confirmed the smooth behavior of the elastic curves after femtoLASIK surgery. Brokenness of the curve can also occur since with a small load 5 and 7.5 gram, the sclera doesn't affect the measurements, but at a load of 10 grams, sclera starts to affect the intraocular pressure readings. At a load of less than 10 grams, the intraocular pressure readings obtained after LASIK are slightly higher than intraocular pressure readings obtained by after femtoLASIK. Here presented numbers which corresponds to our elastic curves for normal pressure and increased intraocular pressure. Some clinical data, they are not so clinical data, and the conclusions I've already told them. So I'd like to thank you for your attention, and I'm ready to answer your questions. I don't hear you. I see that your microphone is turned off. Thank you.
Have you got any questions? So then we thank you once more for your report. Once more, is Malysheva Veronica here?
Yes, I'm here, sorry.
Oh, please.
I will show you my presentation. So, can you see me or can you hear me?
Yes, it's okay.
Okay, hello, ladies and gentlemen. Thank you for introduction myself. Today I want to present you our project is wireless EKG monitoring system with the ability to collect and analyze the received data. So, I think you know that cardiovascular diseases are the leading cause of death globally. About 18 million people died from CVDs in 2019, representing 32% of all global deaths. Of these deaths, 85% were due to heart attack and stroke. And more about statistics, do you know that with heart attack, about 30% of patients die before an ambulance arrives? It's harmful statistic. At the same time, the signs of approaching heart attack appear for a man from 3 to 7 days, and for a woman about several weeks. Knowing the symptom of independent heart attack can increase the patient's chance of survival, and that is why it's really important to recognize infarct in advance. So let's talk about sign of independent heart attack. The first sign is appearance of pain. It starts with uncomfortable pressure, compressive and itching sensation. The pain is wavy, it arises, then it weakens. The second symptom is numbness in the left hand with tingling of the fingers. The next is shortness of breath. It's the most common symptom that develops due to narrowing of the lumen of blood vessels. It means oxygen starvation of organs. Furthermore, it's chest pain, excessive sweating, rapid pulse, edema, sign of cold, snore, dizziness at nausea, and so on. And if we talk about stages of heart attack on an electrocardiogram graph, we can distinguish several stages. First picture is normal. Second picture shows us an increase. Let me take laser. Okay, first picture is normal. Second picture show us an increase in the amplitude of T wave. Next, we see elevation of a T segment and the beginning of formation of the Q wave. It's a Q wave. Then we lost air wave, and after all, T wave is invert. In week or month, T wave normalized, and we see normal EKG with SCA mark. So, the solution of this problem is an invention from the field of preventive medicine based on battery-powered electrocardiogram monitor and built-in signal processor. This device can be used every day, and it can monitor heart rhythm 24 hours a day. At the same time, it analyzes EKG. Built-in accelerometer allows to determine the position of a person in space. It's necessary if we talk about rapid pulse. If person runs, it's normal. But when we see high pulse during rest, it develops into a sign of an impending heart attack. Furthermore, this device can accumulate data over a long period of time. Oh no, what can our invention? Firstly, it can help the doctor identify disease in early stage. Secondly, with this gadget, we can tracking the dynamics of arrhythmia over a long period of time. And as I said earlier, we can determine type of a human activity. And finally, this device has remote communication with doctor and relatives patient. So, how it works? You should wear EKG monitor, which has initial processing for filter signal. Wear my EKG monitor on your body in the rear of head. Next, gadget transfer information to application on the phone, where a secondary data analysis is made. This app also accumulates data from over a long period of time. So, if something happens, app sends an emergency message to relatives and a doctor. After that, doctor analyzes EKG by himself and decide was it an error or patient need help. Of course, in future, it should be done by machine learning. So on this slide, you can see characteristic of developed devices. It weighs a little and it's able to work with a single accumulator for a day. So next, let's talk about our results. On this first video, you can see video from man 21 years old without filter. It's a clear signal with noise. And second video show us signal with built-in filter. And if we compare it, we can see that second video is better, of course. So I also want to show you a video with low quality signal. You see this interval with some noise, and we can cut it from our signal and analyze only clear signal. And I think it's great. It was a signal from man 25 years old. So next, it is our depersonalized database of different sex, different ages people. First pictures show us patient 1 male, patient 2 also male, 20 years old, and 25 years old. So patient 3 female, patient 4 female, 19 years old, and 28 years old. So also about results, we can compare signal from a standard lead with a signal from our device. It was a signal from me, 20 years old woman. Next, let's talk about analysis. Firstly, we try to remove high frequency component with built-in function in MATLAB mathematic package. But if we see first picture is original and second picture is compressed signal, and if we compare these pictures, we see that Isola line is changed and it's not normal. And that is why we try to use Venatovskaya transform without built-in function in MATLAB. And next about it, on this slide, you can see plots of approximation coefficient for expansion using the Beshi-4 velvet. And for better result, we decided to use level 1 approximation coefficient for level 1. And first picture is original signal which we have, and second picture is reconstructed signal by first level of approximation. And if we scale it for C, we see superposition of the original signal and reconstructed by first level of approximation. Their blue signal is origin and have some noise, and the orange signal is reconstructed and it's clear and we can use it. So next, of course, we can use MATLAB also for isolate complex QRS and PICs and use it for next analysis and so on. So let's talk all in all, my conclusion. Firstly, as a result, our team created a prototype of portable wireless EKG monitoring device. And if you see me, I can show you some details of this. This is our prototype. It is EKG electrodes, electrodes with medical material. And it is a battery, small battery. And of course, we have a prototype next, but it is now in university, but I'm not in university. So it was a first. Second, during our researches, our device was tested by 30 patients from medical university. They give us written consent, and of course, all database was depersonalized. The test results showed us that we can compare a cardiogram from standard lead with our device, taking into account the correction coefficient. And the main characteristic of developed device is weight. Its weight not a lot, only 56 grams, and minimum work time is 24 hours. So, in all, I want to show you my project team is Grigory Cherepennikov, Stosh Alena, I'm Malysheva Vernika, and Zaynullina Diana. If you have some questions, you can text me on email or telephone me. So, thank you for your attention. Have you any questions?
Have you got any questions now? Yeah, Malysheva Veronika, and we'll write if we will have questions. Thank you once more.
Thank you. Thank you a lot.
Next report, Shafis.
Yes, hello, my name is Nikita Artamonov, and I would speak now. One moment. Okay. So let's start. As I said, my name is Nikita, and today I will tell you about our study of bone angioplasty of coarctation of the aorta of excuse me, I didn't turn on the camera. 1 second.
The presentation.
Yes. Okay. Now, do you see my presentation? Do you see my presentation right now?
No. Yes, now we can see.
Okay. So my name is Nikita, and today I'll tell you about our study of balloon angioplasty of coarctation of the aorta of a 1-year-old child. Hafizova also, Shasneva Maria, and Patekin Valentin also took part in this work. The aorta is the largest artery in the human body that branches out from the left ventricle of the heart. One of the most common heart defects is coarctation of the aorta, which is characterized by narrowing of the aorta in its midsection. This can be seen in this figure right here. There are two methods of treatment, endovascular and surgical. In this work, we studied the endovascular method, that is balloon angioplasty. The surgeon punctures the artery in the thigh and injects a constant agent into the aorta, which under X-ray helps to visualize the site of narrowing. Then a catheter is inserted into the femoral artery, at the end of which there is a balloon in folded state. Under X-ray control, the balloon catheter is advanced to the site of constriction, and the surgeon inflates the balloon, stretching the aorta. Sometimes, due to too much pressure in the balloon, the aorta ruptures, leading to death of a human. If the pressure is insufficient, then the coarctation will not expand enough, and the operation will be ineffective. Now there are no special methods for calculating the reasonable pressure. So therefore, the goal was set is to select select reasonable pressure in the balloon for a successful operation. For consideration was taken a 1-year-old male child, 75 centimeters in height, weighing 10.3 kilograms. For this child, the diametrical dimensions in the aortic sections were calculated on the special website. In the SolidWorks package, a geometric model of the aorta is built. You can see our model on this page. Here are some diameters we used to use cross-section tool to make it, and also to simulate the operation, the geometry of the balloon was built, which was inserted in the characterization, and you can see it right here. The calculation was carried out in the ANSYS workbench package. The dynamic, hydrodynamic problems, as well as the contact problem was the contact problem of static were solved. The hydrodynamic calculation was carried out in ANSYS CFX when constructing a hydrodynamic grid. We use the Tetrajon's method, and the mesh thickening at the edges is also set it up with the inflation tool. You can see this inflation right here. Next one, the dynamic calculation was carried out in transient structural, where here the Tetrajon's method was also used to create the mesh. To set the boundary conditions, so for the walls, a material was created in which the density, the Young's model, and Poisson's ratio were set. The interaction of blood and walls was specified using a fluid-solid interface. You can see it here with yellow color. A termination condition was set at all inputs and outputs. So here they are with the blue color. Boundary conditions for the balloon. The material of the balloon is nylon 12. Using the displacement function, we make the displacement changes only along the x-axis. The pressure of 5 megapascal is set on the inner wall of our balloon. To set the boundary conditions for blood, the no-slip wall condition was specified. All 4 outlets, so this free one and the last one here, have a 0 pressure condition with the outlet option. At the entrance here to the artery, we set the rate of blood pulsation from time for a 1-year-old child that we're looking for, and the graph of the blood vessel, the blood velocity is shown here. You can see it. The results of dynamic calculation under the aortic under the action of a pressure balloon, the diameter of the characterization segment increased by 2 millimeters, with which is 30% of the diameter of the healthy aorta. So that's the result we wanted to have. The displacement of the walls at the time of systole is maximum since the heart contracts and the maximum release of blood through the aorta occurs. In diastole, no movements are observed. Due to the narrowing, the blood cannot pass in a uniform flow. Therefore, increased pressure is created on the walls, which is why the displacement values are high. And this doesn't happen in the operated aorta. So now let's talk about the last results we've got. So on this page and on the second one, we have results on the left pages, on the left images, the results before operation, and on the right images after operation. So on the first page, we can see the pressure. On the second one is velocity. So let's talk firstly about the values before the operation, results of hydrodynamic calculations. So at the moment of systole in the area before coarctation, the flow collides with the wall, due to which the pressure reaches its maximum values. In the coarctation segment, the velocity reaches its maximum values, and the pressure reaches its minimum due to the narrowing of the area. At the time of diastole, pressure and velocity are evenly distributed through the aorta. Now let's talk about results after surgery. So here the blood moves more freely. In the place where previously there was coarctation, a zone of low pressure no longer arises, and the velocity at the moment of systole evenly distributed, except for areas of natural narrowing where it's higher. From these distributions, we can conclude that the operation was carried out correctly. And let's talk about conclusion that we have after all this work. So first of all, the aortic geometry was constructed to approximate reality. Second one, a reasonable balloon pressure was selected, at which the diameter of the coarctation segment was increased by 30%, and this allows the blood to move freely in the aorta. And the last one and the main that conclusion of our work is that given the elastic properties and individual size of the patient's aortic wall, we can run simulations to determine a reasonable balloon pressure for the operation and reduce the consequences and risks. So that's all I want to tell you today. Thank you for your attention. If you have some questions, please ask me.
Have you got any questions? I think you should also represent your email address for any case, maybe.
Yes, I think we.
Let's translate.
Mm-hmm.
Thank you once more. Ученицкий is here. Is here. Please. Begin. Мы не слышим вас. Пожалуйста, поправьте, что там у вас не работает. Так, вам время. Вас не слышу. Вы можете тогда отложить, поработать со своим компьютером, а мы послушаем другой доклад. Из Ростовского университета я предлагаю послушать вот доклад Шадрина. Да, правильно? Садырин, извините.
Good evening, dear colleagues. Let me introduce myself. My name is Sadyrin Evgeny, and today I'm going to present you some results of the joint research between the Laboratory for Mechanics of Biomaterials of Don State Technical University and Rostov State Medical University from Rostov-on-Don. And the theme of this research was stated by Professor of Dentistry, Stanislav Maksyukov, with Professor of Dentistry Biomaterials Research Unit, Michael Swain. Their research is on influence of dental treatments on mineral density of white spot lesions using X-ray microtomography. So for the colleagues who are not very well acquainted with the tooth structure, will be short beginning of the presentation. So we'll talk mostly about the talk mostly about the two tooth tissues, namely enamel, the most hard tissue of our body, covering the dentinal crown from the top, comprised mostly from inorganic material, and underlying dentin, which makes the bulk part of the tooth. It contains less inorganic material, but more organic material and water. So its main structural feature are the dentinal tubules, and this is the tubule from the longitudinal cross section. Between them are collagen fibers type 1. So these images were obtained from our SEM unit. And here is a single collagen fiber. And it's a short movie how the dentinal tubules run through the dentin made on the X-ray microtomography machine. So yes, they run through the whole dentin from the pulp to dentin cementum junction, transporting the nutrients to the tooth tissues. And it is the main structural feature of enamel, the hydroxyapatite crystallites, very small crystallites of 60-70 nanometers in length and 25-30 nanometers thick, each covered partially with protein enamelin, which enables them to glue to each other, forming another level of hierarchy. Enamel rods or enamel prisms, looking like really mountains. On the tooth surface, the special biofilm emerges, which is called dental plaque. Some bacteria, among them the carcinogenic ones, can settle in this biofilm thus consuming the carbohydrates in the oral cavity, producing acids, and thus lowering the pH locally in the enamel. This process is called demineralization, and it is the continuous mineralization is dental caries. The first visible clinical stage of caries is called white spot lesions. At this stage, the subsurface body, so-called body of the lesion is formed. It is enamel where the crystallites are partially demineralized, either on the periphery or in the centers, as was shown in the classical paper by Nagasawa and Miyake. And at the top of the lesion, in the tooth surface, the hard remineralized pseudo-intact layer is formed. So the dental clinicians can see this stage of caries as small whitish opaque spots. And here we can see such a spot in the optical microscope. There are several techniques to treat this disease, but our colleagues from the medical university names three of the most popular. Two includes sealing with composite material, glass ionomer cementum, and one most modern, minimally invasive method, infiltration technique. And the global question is, which of this method is the most effective one? Of course, it's not very easy to answer this question in a single research, but we had a task with the following aims: to establish the protocol for ex vivo comparison of teeth before and after treatment with these techniques, to find out the influence of the treatments of the mineral density of white spot lesion regions, and to find out if treatment restored the structure of white spot lesion area at the microscale. We had a number of extracted samples from which our colleagues from the medical university selected 5 samples with the same white spot lesion stage according to the matrix of the World Dentist Federation. Following extraction, the samples were kept in the hypochlorite natrium solution for the disinfection reasons, and then were put into the Hens balanced salt solution into the fridge. So here you can see the scheme of the experiment. First of all, the clinicians gave me the sample. I scanned it in the X-ray microtomography unit, then processed the sample using the special software, then gave back to the clinicians. They treated the tooth ex vivo and then gave it back when the microtomography and processing were made once more. After that, we obtained 2 3D computed models of teeth, which were put one onto each other by the spatial coordinates and analyzed. So here we can see our machine. It's called Zeiss X-Radia Versa 520. The sample is put into the small tube on the holder between the X-ray tube and detector plus objectives with the scintillators. So the sample rotates on the small angle each time. We take the projection of the sample, and then we collect these projections and reconstruct the 3D model of the tooth. And the parameters for scanning are listed in this slide. With each sample, we scan also special etalon sample, which is called calibration sample or calibration phantom, comprised out of 4 glued parallelepipeds with the materials plastic, magnesium alloy, aluminum alloy, and fluoride. This enables us to convert mean gray value obtained as a standard for the microtomography to the mineral density. So after processing of these microtomograms in the volume graphics software, we can cut the 3D model and the stacker virtually without destruction at interesting sites. So for example, this is the first sample treated with glass ionomer cement. So this inset is how the enamel looked before treatment. The colors correspond to the mineral density map and the mineral density scale. You can see on the level on the left part of the screen. Here is glass ionomer sealant. We took the regions of interest by the cylinders of the dimensions that can be seen on the screen and compare them to the healthy tissues. As for this sample, we had 2 areas of caries. We studied both of them. Here we also took the small regions of dentin bordering enamel as close as possible to the white spot lesions. We also can look into the structure of the sealant. Our dental clinician colleagues were very surprised to see that there were a lot of inclusions and pores in it, and the biggest one can be seen on this slide. Here are the results for the first sample. But the main conclusions here is that density of sound enamel was not affected in the both white spot lesion focuses, and another white spot lesion of glass ionomer cement affected dentin. So this is good and predictable. However, there are interesting points according to the caries itself. Caries lowered the mineral density to approximately 5% in the cusp focus. However, the sealant had even less density. It was lower to 12.5% compared to the healthy enamel. And the same, practically the same picture was for the medial focus of the caries. So you can see that glass ionomer cementum is lower than the natural enamel. This gave us interesting information to compare glass ionomer cement with the composite material. Here we can see this the composite material sealant, and this is how this area looked before treatment. We can see that the composite sealant is comprised of 2 layers, the outer one and the inner one. So they demonstrate different density, and we decided to study them as a whole, the outer part and the inner part separately. We found out that density, first of all, of white spot lesion enamel was lowered by almost 14% compared to the sound enamel. The averaged mineral density of the sealant was lowered by 3% compared to the sound enamel. However, the outer layer of the sealant was almost perfectly resembled the natural healthy enamel, whereas the inner layer was slightly less dense, up to 5.63%. In this case, neither white spot lesion or composite seriously affected dentin, both found dentin and both dentin bordering white spot lesion, as well as on the previous sample, and it's also predictable. However, the most surprises were for the infiltration technique. For example, for the first, a few words how the dental clinician performs this procedure. First, she tries to remove the hardened remineralized layer by the acid. Then she fills the body of the lesion with the polymer, applies polymerization lamp, and the basic idea is that the partially diluted crystallites are now filled with polymer and does not contain water and does not have space for carcinogenic bacteria. But the most surprise was that all the tissues after the treatment demonstrated lower density than before the treatment, than caries tissues, and also in the sound counterparts. And the working hypothesis was that the dental clinicians put the acid not very accurately and affected the surround tissues. So we decided to repeat the experiment on another sample. It had its own peculiarities. The most obvious was that the carriers demonstrated 3 different zones connected with the low demineralized enamel, and we studied all these 3 zones. We found no significant effect of carriers on enamel density quantitatively in 2 of the 3 zones. And in zone 2, carriers has reduced the density by 4.15%, and in none of the zones did infiltrant noticeably increase the density of enamel. However, it did not decrease either, and this results was rather good for our clinicians colleague. They say that we can assume that this, although the density did not increase, it is now free from carcinogenic bacteria, and in the everyday life, during the remineralization process, it may increase in the oral cavity of the patient. We also made the 3rd control 1 sample for the infiltration technique, and it unfortunately did not make us very happy, because this picture on it was at the same as the sample 3. Even here you can see that prior to treatment, the density of enamel was higher even visually. It is because we assume it because from the following reasons. The spot of the carriers was too small. It had strange trajectory. It moved through the cervical area. I tried to make some kind of movie here. It moved, it was prolonged to the cervical area, and moreover, it rotated along the dentine enamel junction. So the dental clinician could not understand this, even using the optical microscope in the clinic. She tried to remove the remineralized layer and put the infiltrant as much as possible inside this spot, but presumably she damaged the surrounding enamel. So we do not see the decrease in dentine here. However, we see unfortunately decrease in the carriers area after treatment and in surrounding healthy tissues. We also assume that it happened because of the acid, which worked not as intended. So some of the results are listed on the slide. We established the protocol for ex vivo comparison of teeth before and after treatment using microtomography, traced the influence of 3 treatments on mineral density of the regions. The most interesting results for the clinicians were that the composite material is better in terms of restoration of mineral density, as it resembles the natural enamel in terms of mineral density. However, the glass ionomer cementum has some also possible advantages that needs to be further researched, and acid from infiltrant set may damage tooth tissue seriously. So the infiltration technique is the most difficult one for the clinician and demands high skills from the doctor. Thanks a lot for your attention. If you have some questions, I will be happy to answer them.
It is interesting for me what your result help for medical in our country to help children which fail.
Thank you. Not now. Игорь Кульчицкий, наладилась техника? слышно.
I'm here. Can you hear me? Or not?
Да, вы слышите.
Ура, ура, finally. Так.
You could 15 minutes, please.
Am I beginning?
15 minutes.
Thank you. Hello, my name is Lekszycki Igor. The topic of title is algorithmic modeling of the heart based on CT scans. Let me start with the issues. Issues according to WHO, only on 2008 year, 1/3 of all deaths are because of cardiovascular disease. So timely and high quality examination can reduce the number of cardiovascular deaths. One of the options for survey is CT scan. However, it can be time-consuming for doctors to analyze the image alone. They can miss some details, underestimate the physical size of the organ, and there is no opportunity to practice the procedure in advance before the surgery. And I would like for doctors to be able to do that, so that it would be a lot easier, faster, and better. In this regard, my main goal is to develop an algorithm that allows using CT scans to simulate a heart or 3D body suitable for printing on a 3D printer in reasonable amount of time, not more than an hour, using programming methods. And to achieve this goal, the following tasks: study CAT digital image storage formats, study 3D model storage file formats, develop an algorithm for full image processing and for creating 3D models, and finally test the algorithm for and compare the results with the ideal model and determine the quality of the pathology conveyed by the algorithm. On the right side of the slide, there is a block diagram of the choose activities that were carried out in this work, which are three main blocks: image processing, creation of the 3D models, and post-processing. Python was chosen as the main programming language because of its simplicity and the vast amount of literature that could be found in the public domain. And the first thing I learned when the CAT scans were obtained was they were, as it turned out, they store a tremendous amount of data beyond what I needed. And each slice was stored as 2D matrix with numbers, where each number is proportional to the density at a given point in the volume. You should understand that CAT scans are based on X-rays, so the organs are hardly visible and difficult to discharge from each other. And just to fully process the image, I needed to increase the contrast of the image, normalize the values of the numbers, and determine the space where the heart is, as well as the range of the numbers. Based on the data I had previously, a full processing for the images was done using the appropriate libraries to do this, such as FIDICOM, OpenCV, and NumPy. Everything that was not related to the heart was painted black, and the rest was left. The values of the number in black equals 0, the rest are positive. It's like X-rays picture. After the image was prepared, all information was sent to the Martian Cooks algorithm. This is common algorithm for solving this kind of problems. In general, this algorithm looks at values of numbers of points that make up the minimum volume element, corresponding to the grid partitioning. In this case, the partitioning grid was cubic. If the values of the number was positive, then it's considered that the point is inside the object, and with this rule, 256 different boundaries appeared. But because of symmetry, there were only 15 unical boundaries plus 3 additional boundaries to get rid of voids in the body shell. This slide shows these unical boundaries. That is the rule itself. Using this rule, we kind of march through the cells and build the body shell. After the entire envelope is built, it is saved in OBJ file format. This format was chosen because it's compact and widespread. First, we list the coordinates of all the vertices, and then we list the indices of points that make up the polygons. The following hard shells were obtained using this algorithm for the outer and inner shell of the heart. Here you can see clearly the shells of heart, as well as some extra mesh objects such as ribs. Next was post-processing. I used the modeling package 3D Studios Max, since the modeling package was familiar, and this modeling package provides Python code for all its tools. This step merged repeated vertices, remove extra mesh object, filled voids in the shells, smoothed surface, and merging the inner and outer shells of the heart. The slide shows my model and compression model. Unfortunately, only one pictures are preserved. But in this version, you can compare the two models. They are similar to each other. The compression model has additional branches of bases. I got rid of them during post-processing. And also, the compression model asks the internal structure of the body. And most importantly, my algorithm still allows me to convey the internal structure of the heart. The slide shows a slice of the final model, as well as schematic of the heart structure of image heart. Since the CAT scans was done on infant, I expected a corresponding heart structure. The pathology of this heart is hypoplasia or reduction of the left heart in the since the hypoplasia of visible. There you can see pathology in this area. It should be noted that the CAT scans do not show the values, so they are not present on the model. I also consulted a cardiovascular surgeon who said that the result was correct. And during this work, the following tasks were performed. It's CAT digital image storage formats for studies and formats 3D models, develop an algorithm for complete image processing and created that allows obtained 3D body from CAT image. The ideal model was compared with the results of the work, and 3D body with the fully transferred internal structure of obtained by means of programming methods, the processing of the image and further creation of the 3D models was accelerated without the post-processing. The algorithm created a heart in 3 minutes or 9 minutes. post-processing took me no more than 10 minutes. The resulting third model is suitable for printing on 3D printer. Thank you for your attention. Maybe you have a question?
Thank you.
Thank you for an interesting report. Can you please tell, in your opinion, which format is most suitable for 3D printing nowadays? Is it DCOM or maybe TXRM, or according to your study?
I have format DICOM and that images that I have that I had was so hard structure and have more noise. I tried to fix this problem and finally got value.
We can say that you modified DICOM format a little bit, reduce noises and to process further.
Modified. Maybe now I can answer on your questions.
Okay, maybe we'll discuss this later. Thank you very much.
Thank you.
Thank you once more. Next report is here Varvarkina. Please. And processing of motor cortex.
Good day, ladies and gentlemen. My name is Ekaterina, and this is Valit, and we're here to introduce our research project, which is electroencephalogram modelization and processing of motor cortex EEG signals for biomechanical applications. So the core subject of our project is motor cortex, and we would like to explain you how we can apply signals of the motor cortex for motor imaginary neurocontrol. I'm sorry, it's not loading. Yes. So why is it needed? It is needed for people with spinal muscle atrophy. This is a genetic disease that causes damage of neuron covers of neurons. And by this, starts generation of muscles. So these people can't really move in their teenage. So when they grow, they lose their ability to move their parts of the body. And right now, only system that is used for them to control some kind of armchair is implementation of alpha and beta rhythms classificator. To move right, it's concentration mode. To move left, it's meditation mode, and so on. And it is not enough to have better quality of life. And for this reason, there are many other applications that are much more difficult. And we would like today to introduce pipeline of EEG processing with dry electrodes equipment that can help to improve their lives.
So EEG signals can be really tricky and hear me? So EEG signals are so tricky, and they can to process them. You need to go through this pipeline represented here, and this is the first presentation. This is first processing of the EEG signals that anyone can have to pass by. So how we can do it? So the first thing is to collect the data using CAP channels, and after collecting them, we are using the help of the EEG lab, which contain a lot of algorithms that can help us with this. We import the data, and then we try to find the channel locations and see if they are connected properly. And after this, we can plot it in 3D to see if they are connected. They are exactly as we put it. Then we apply a reference for our data. The reference can be done by two, whether referencing based on channel, then interpolate it, or use a computer average referencing. Then we need to do a filtration for our data. The filtration is based on our data. When we look at it, we can understand if we can play high or low edge frequency at first step. Then we do a resampling for some computer reasons, as it is here. Then we can apply the spectrum, and we see where our motion is manifesting. And once we detect it, we can go by removing the artifacts. Since EEG contain a lot of artifacts, we enter the parameters, and we can remove the artifacts that we don't want to be inside. Once we detect them and we reject them, as to present here, and we can go to do running the ICA. So ICA, basically what it's going to do is like to decompose the source of the brain activities based on the source activity exactly. And then we run the ICLab, which gives us the probability of each activity involving in the brain itself. Then we run some additional artifacts removing by using the algorithm called MARA, which can remove some artifacts that we didn't see by eyes. Like for example, here, it can give us the probability. So our project was to we deal with two types of motions, which is the real motion, the imaginary motion. We can see here the real motion manifest here. And then we try to detect the imaginary motion. The imaginary motion was really hard to detect, so we had the subject to put the subject in some sort of testings using two types of tests, which is the meditation and the concentration. And we can see how the concentration level is increasing in the subject. Then we do the recording of the brain again to receive the imaginary motion.
So here we'd like to introduce to explain how mirror control systems work, but it's video also. Yes, so in mirror control systems right now are the most advanced control system, and we can provide a variety of different motions. And as you can see here, it's really good quality of motion provided. And for this, we need to apply good control systems. And here with muscle signal, it's pretty simple. And can you turn on this also? So with muscle signals, our brain can provide the signal through the muscle spinal cord to the muscle, and even if the arm is damaged, we still have muscles and nerves up in the upper parts of the body, and the quality of signal is pretty good, and the amplitude of signal is pretty good, and we still can understand which nerve can provide the signal for which motion. And so classification is pretty simple, and dry electrodes are good enough to understand this kind of motion. But for second case, for neurocontrol with the brain, it's much more scary thing. So right now we need to do special cranial operations, and it's recovery process is pretty long and hard. And today, to apply good quality of the signal of EEG and to understand it right, they do lots of special operations, and you never will know will you be able to control your arm or your or another device by this, because you need special neurotraining to understand is it enough or not. And in our case, we would like to introduce another technology of implementation of dry electrodes. And in our case, we used simple equipment, 8 electrodes. It's not really enough, but still, it's for the beginning, it's the most the cheapest way for us to do this. And we tried to extract signals of motor cortex from this kind of equipment. And there are many minuses. So dry electrodes, they have high contact impedance between the sensor and the skin. There are more EEG artifacts and noise that we need to clean. And Valit just shown that we did this in the pipeline. And the signal quality is questionable, but still there is right now a big correlation between signals of dry electrodes and wet electrodes. So today, with technologies of working with signal, we can provide the similar result with wet and dry electrodes for today. But it's cheaper, it's more easy to set up, so we can just bring it to any patient in any kind of state. It's portable, and it's able to replace recording to patients or investigators' homes. So we also did some kind of research in our homes because of coronavirus, and it was more simple. And for these reasons, dry electrodes, the technology is harder to implement. There are many issues, but because of all these pluses, we can do variety of research and implement different methods to receive the same, to solve same neurocontrol task.
So we know that the EEG contain a lot of artifacts, a lot of information from the brain. So we had to know, once we detect our motion, we need to know how we can define the connectivity between each part of the brain, how our motion is really, the information of our motion is really manifested. So there is some type of algorithm called SIFT, which is like source center interaction between like the components here, and it has this own pipeline which gives us the model. Once we apply this, we can and we process our data again, we can find and look to this type of matrix here, which shows us like the flow information between each components, and this will lead us to define and localize the exactly source of the motion and how it is moving, and how and to detect it, which part of the brain it's really working on this motion. And it gives us also the frequency of the motion, and we can extract it easily. And after that, we can apply also a 3D map to see exactly, which here presenting by pipeline, by some sort of canals. We can see how the activity of each motion by time is manifesting and how it's moved from a part to a part. This helps us to detect, and we were using the DT-TFT-08. So there are other of type of connectivity estimator that we can use, but this one was the best one to detect the motion. talking about this will lead us to, in our experiment, we were done upon 3 persons, and we can see that the source of the motion activity is different from a person to another. This is subject number 1, and this is subject number 2. So BCI is really a good feature for us to study the EEG signals, but it's not really enough. So we had to implement what the other classification which come after these steps we are presenting. So there are feature by feature extraction or by feature classification. However, this type of features have some sort of a huge amount of error at the end when we apply them. So we can go using another feature, which is a convolutional network. So what we are going to do here next is like to convert the EEG raw data to imagine representations in a multi-layer of frequency band. And then we create a CNN model designed for this specific motion. Then we need to apply a huge amount of recording data sets. We need to have them for each motion. Since the sources are so close, so the error might be so big, therefore we need to apply a lot of amount of huge data sets to work with that. So, thank you.
So for conclusion, we would like to say that our topic is research topic, and the classification is still the task that we need to solve. And we'd like to say that we would like to encourage scientific community to also do some kind of research in this area, because classification methods there is huge amount of them, and as equipment is cheap, and we have all the resources to do such kind of simple research. We would like to encourage you to also join to this kind of research and to improve quality of life for people with spinal muscle atrophy and another kind of diseases. Thank you.
Have you got any questions? Thank you once more. It was very interesting, but I think it's very difficult just now to ask some questions. Thank you. Тоже будут вот.
So, dear colleagues, my name is Radchenko Igor. I will make a small lecture on behalf of our leader, Sukharukov. He is at the moment in Moscow, and because of our COVID reasons, he delegated me the possibility to make a small lecture for you. One important point, I will present a huge bunch of experimental data with our own explanation, our own results, but one of the main idea that there is a huge lack of explanations in the sense of mathematics or probably even mechanics. As soon as we have to be close to biomechanics, as I said, I will present you lots of biology, and we will need probably big or huge even help from you guys, if someone would be interested, to take a part in the explanation in a sense of, as I said, theory and basically mechanics and whatever. So my task to present you ideas on multifunctional microstructures for encapsulation, sensing, and remote control delivery. In this case, on biochemicals and biological cells. First of all, remote control microstructures. What does it mean? Normally, our body is huge vessel or huge amount of different cells, tissues, material, liquids, and whatever. And in some places, from time to time, they appear as small problems, disease, inflammations, and whatever. And ideal situation would be to have somehow, we call it sensor submarine. So idea that we have a small micro but really intellectual object that could drive in a certain place where do we need it, make a small task there, and then in ideal case go somewhere out of the body and without any extra or negative effects. So what are the ways how we can have this remote control? Magnetic field, one of the obvious ideas, optical addressing, ultrasound, or last our achievement shows that it's also possible by means of radio frequency and even FM. So just idea, our structures is a sphere with normal size from let's say 50 nanometers to 50 microns. That is in most cases done by means of polymers with more or less empty inner volume. Idea that this volume is more or less empty because normally you can easily functionalize this interior of this object, of this capsule. You can put there lots of drugs, address materials, or just something sensitive and whatever. So somehow you can functionalize this sphere to provide the additional functional possibilities. So from one point of view, there is just minimum chemical modifications that needed to create this object. This could be kept responsive for external forces and whatever. And normally you can even create the normal productive procedure to create this object by means of self-assembly. And at the moment, the easiest, let's say, way that we create these objects just by means of layer by layer deposition of the differently charged polymers. So about the function. This object can be, as I said, easily modified on the surface. It could be modified in the structure of the wall. And of course, it could be easily modified in the interior. As a result, you can have, from one point of view, as I said, remote activation of this object. You can create it permeable or semi-permeable, or you can even switch this possibility. As a result, you can have control release. You can address this object by means of external magnetic field because of magnetic nanoparticles, if you would need them in the surface. You can even create a microreactor by means of this object, just by means of modification of this inner volume. So lots of different possibilities for this object. So I won't spend too much time on the ideas, how you create it finally, what could be the different ways. Just believe me that there is more than 10 different ways how to create more or less productively or effectively this type of the objects. In our case, we use normally coaxial electrospray, microgels, or just normal layer by layer, as I said, on the base of the inorganic crystals. So another important point that could be used for these devices is modification of the living cells, because probably you know that our immune system is extremely, say, extremely hard in a sense of wars against the external objects, and idea to put our microspheres or microcapsules with functional ideas into the cell is just one of the perfect ideas to keep the immune system not intact in this case. So just nice example, capsules that are uptaken by the living cell. In this case, it's more than 10 capsules. They were modified with a special fluorescent object, special fluorescent dye that could make for us easier to trace them. So just a few words about the possibilities, how we can change the permeability of the wall. In this case, it's a different pH, could be light, temperature, different salts and whatever. And as a result, we can, as I said, easily modify the inner interior of the of these microcapsules, can create them permeable, and as a result, encapsulate something impermeable to keep this inside, or in this certain case, just open the capsules and release the encapsulated material. In this case, it's just easily triggered by different ways. The capsules itself are also really easily controllable in a sense of mechanical properties. Somehow, for example, you can create the inorganic cores. As a result, capsules became extremely rigid, more or less close to the crystal formation. From other point of view, these crystals inside could be easily dissolved. And as a result, these capsules just became really, really thin, just, I think, something like 20 probably nanometers thickness of the biodegradable polymers. Just easy modification, and these biodegradable polymers with size and shape of the sphere would become a ball, extremely rigid, and even upon the drying, it keeps its integrity and their inner modification also. One of the ideas to create a more rigid is calcification. As a result, by means of temperature, we can have monodisperse with certain porosity inorganic cores. Another way to modify them is incorporation of the magnetic nanoparticles in the wall of the shell, or if you would need it more magnetic, more responsible in the sense of magnetic field, we can create particles in the inner interior of this object, and they'd be, as a result, even much more magnetically responsible. Another way of activation of this object is infrared laser. So somehow we can exclusively open certain type of the shells, certain type of these objects, and as a result release the drugs that are kept inside at that moment. Another idea to make this object more functional for the certain applications is siliconization of the wall itself. Probably you know that polymer films themselves are relatively permeable for the small, at least, ions and whatever, and at least for water. And modification of the wall with silicanes, it gave us the possibility to make the walls just absolutely impermeable even for water. So somehow if you want to keep the drug into the capsules, you can put it, then modify the wall of this object, and result this drug and solid will be kept as long as you want. A nice point in case of silica is that silica is extremely responsible for the ultrasound, and nice idea, nice potential application that we have used already for the certain medical cases. Drugs, in that case, it was adrenaline, was kept inside the capsules modified with silicane, with silica in that case. Then exclusively in a certain place of the body, this ultrasound was applied, and only exclusively in this place, the capsules were destroyed, and as a result, drug was released. So it's one of the approaches to get the targeted release of the drugs, or targeted delivery of the drugs. So that's the demonstration of this ultrasound simulated release, just for you to show that really usable and effectively workable procedure. More or less the same, but just inside the living cells before the rupture of the capsules on the left side. Yeah, here. On the left side of the image, you see that capsules that are red. So somehow the cells, living cells, are just normal. And after the destruction of the capsules, we can see that more or less the whole cells became red. So the fluorescent dye that was as a marker in this case kept inside the capsule, so it released, and the material that we wanted to give to be transported to the interior of the cell. So this material is more or less diffused in the whole cell. Another way to change the thickness and mechanical properties of this object is modification. Another way of modification of the walls of these objects. In this case, it's carbonization by means of temperature and certain pressure. We got finally much more rigid, much more thick structures that, as I said, good way to change their properties for the certain exact applications. So once again, different ideas, different ways how you can control the permeability of the wall. Even for the rhodamine, it's dye with approximate size of few nanometers. I think it's weight something like 500 or 600 Daltons. So, and for normal polymer films, this dye is easily permeable. In case of carbonization, we can trigger the thickness and as a result permeability of the wall. So capsules became impermeable for this material, even for these really low and small molecules. So a few more words about magnetic delivery. Basic idea that magnetic nanoparticles are incorporated into the wall of the capsules, and as a result, you will see experimental ideas. So basically, idea you have a blood vessel, you have a magnet that is incorporated close to the vessel. So, and our results show that experimentally, in case of application of the magnetic field, we can control the amount of the magnetic, and as a result, in our case, it's fluorescently labeled our particles that we can greatly increase their concentration exactly to the vessel wall close to the magnetic field, I mean to this magnet. And nice point is that when the field, external field is off, we have more or less controllable release of the trapped material. So idea, you switch on the material, you switch on the field, most of the capsules stick to the wall, so we can control them, we can keep them as long as we want. And as soon as we want to release them, just switch off the field and all capsules continue their floating ways. That's the same just inside the mouse. So that's the real tissue of the mouse with real blood vessels. So that's here you see that upon the application of the field, you have the huge concentration of the fluorescent capsules exactly to the close, I mean, to this external field. That's for a mouse, just to demonstrate you that here was injection of the capsules. Most of them, of course, at the moment sticked to the their, in this case, to the liver, but upon the application of the magnetic field, you have a relatively recognizable amount of the capsules of fluorescent as a result of the capsules with, in this case, with dye, but just a model. Normal idea that with the certain usable drugs, so this amount easily, I mean, you can easily pronounce that idea and in fact, concept does really work. Activation of the capsules, I mean, ability to control the permeability of the capsules wall, and as a result, idea to get the different results with the capsules as sensors. In this case, we have dye that pH dependable. So in case of pH 6, it's green. In case of pH 9 became red. So you can, as a result, use these capsules as a sensors of the interior weight applied at the moment. For example, here we have living cells. You can see them, and before the uptake, our capsules, they are slightly red. It means that pH is pretty basic there. But when the capsules get into the living cell, it changed its color, and as a result, it means that it changed the pH around the capsules. So somehow capsules became a sensors of the local pH of the tissue in that experiment, just to demonstrate you. Magnetization of the living cells, more or less the same idea. Capsules, as I say, they can be relatively easily incorporated into the living cell, and as a result, these capsules, when they have a magnetic properties, the living cell with the capsules also get the same properties. So somehow you can at least trace or even separate the living cells with the capsules as a result with magnetic nanoparticles and without them. Basic idea, as I say, it's more or less the same. Capsules, living cell, as a result, this composite object of the living cell with the capsules, and nice point, upon the applying of the external magnetic field, we can force or we can drive the living cells to the certain place of the interest by means of this magnetic field. That's the idea of how to sort the living cells by means of magnetic nanocapsules, magnetic nanoparticles. Idea is the same, external magnet. And as a result, capsules with magnetic modification and the cells with magnetic modification will be sticked to this vessel, and only objects without magnetic modification will come through. So that's the idea, as I say, to easily separate living cells with and without modification. Just to show you small nice results on the magnetization and delivery of the stem cells. Probably you know it's one of the potentially most interesting ways in biology, usage of the stem cells for the different treatment of huge amount of different diseases. So this magnetization as a result, separation and modification, it's one of the potentially interesting ways to use this approach to the stem cells. So that's what I explained you already, idea of the magnetization and separation. That's the living cells that are modified with the capsules, and this result, so most of them there, that's living cells that were not modified, and as a result, they just come through and are not in the interest of our experiment in this moment. Drug delivery, I won't spend too much time. Idea is more or less the same. Stem cells, capsules are modified with the certain drugs or certain functionality. And as a result, for example, living cells that are modified with the capsules, they became much more informative, productive, and whatever. At least they were modified in a certain way. And even in that comment, at that moment, it was the model ways, model drugs that force the cell to create the certain type of the dyes. So in that case, we force the living cell to create the dye with the blue color. Microchamber arrays, it's one the same idea, but on the planar structures, multifunctional structures that are made in the form of the film. So the same idea, as I said, multi-layer functional objects that has finally the planar structures, and as a result, their functionality. That's more or less the same idea, the same approach how to create them. That's electronic microscopes of these structures with different thickness of the walls. A nice point is that these structures are empty inside. So just for you to show that how does it create normally, what does it work. And nice point that this empty volume is really easily modifiable by external drugs, materials, functional molecules and whatever. So somehow it's just a huge potential to be used for the different approaches that would be needed to be planar. More or less with the same, with different modifications, different ideas, what should be changed, thicknesses, sizes, shapes, and whatever. As I said, they are easily controllable in lots of different applications, empty inside. That's even nice for you to show that they easily kept to be the film, and all these small volumes that could be, as I said, modified with more or less any types of the drugs, materials, functional nanoparticles, and whatever. Depends on the application that could be needed. Different ways, different polymers, as I said, biodegradability, biocompatibility, or stability, or whatever. They could be even inorganic, finally. They could be loaded, as I said, with different types of materials and different type of functionalization. That's the way how normally we do it in our laboratory. That's just for you to show that the materials that we applied there are inside. That's crystals of the rhodamine, just let's say, as a proof that they're really inside and the procedure really works. Films with the same idea, the same cases, same approaches. These films are controllable by means of different external forces. In this case, for example, ultrasound can also easily rupture these structures. And for example, one of the exact applications that we control at the moment, or we can try at least to apply, it's stents or implants with this that are covered on the surface with these planar structures. And all these small vessels, they are modified with certain drugs. And for example, in case of inflammation, you can just slightly expose this place of interest by means of ultrasonication, and the vessels destroyed, drugs released. And for example, it's one of the easiest way to force or to fight against the inflammation exactly that is localized close to the implant. That's a demonstration of this approach. Again, the same mouse with the same idea. In this case, just probably if it would be interesting for you, there was a film with film that is modified with adrenaline and approach by means of sonication and whatever. I mean, destruction of the these vessels and free of the adrenaline result finally in changes of the blood pressure and blood flow rate of the mouse. So somehow just for you to demonstrate that idea to release the drug and change the life, let's say, or change the situation inside the living body, it's already achievable, and we can have already certain results in this way. That's the same idea, and just in the nice images. These vessels can also be destroyed by means of laser beam. For example, in this case, 2 points where the laser was applied, and as a result, only these small volumes, only these small vessels were destroyed, and the drug released from there. All other places stays intact, so that were not destroyed, and drugs there still kept inside. Image to show you the same idea on the most size. That's exactly the place where the exactly this vessel was destroyed, and just for you as a model, only kept in this place drug became free. I mean, was free, and as a result make a certain, let's say, medical application. All others, I mean, all other vessels stay still closed, and drugs there kept intact there. The same idea on the way of living cells, cells with this structure. Upon the laser beam, we released the drug only exactly in this place, and the result, the living cell was modified, all others stay the same. Microchamber arrays for sensing. Idea is more or less the same. Nice point that these structures, as soon as they're periodic, they have a diffraction, and as a result, you can use them as a sensor for the external conditions. For example, as soon as we have a polymer, we have a periodic structure, by means of diffraction, we can easily control what's the conditions around this film. For example, there is a number of materials that are pH sensitive or pH responsible, and as a result, upon application of the different ways of pH, we can see that diffraction structure of the laser beam, it changes by means of external conditions. So it's the way to control the somewhere, I mean, at least in this case, pH for the external ideas. The same idea with the temperature. Lots of polymers are temperature sensitive, and as a result, for example, it's one of the nice applications that we plan in our heads. Certain type of the food that cannot be heated upon the certain temperature. So you can easily use the same nice point that these structures, as soon as they're periodic, they have a diffraction, and temperature became higher than certain level. In this case, for example, even once, just once, we have a temperature above the 61 degrees centigrade. As a result, we lost all the structures. For example, I mean, your food stays somehow, you think that it's the same, but this sensor shows you that no diffraction, no periodic structure, as I said, no diffraction, and as a result, you can easily say that, okay, your food is not good anymore because once it was heated above the allowed temperature. Just to demonstrate the same idea, diffraction structure that we had before the application of the temperature, and that's what we have after. No diffraction just because of destruction of the periodic structure of the film. Last words. As I said, there is a huge bunch of experimental data, but we still need lots of theoretical and even the at least mechanical explanation of all these effects. We can answer the question what would happen if temperature become above the certain level, or what would happen if pH become different or greatly different from certain levels. But we still need lots of at least theoretical data, theoretical models to explain what's really happened in the film itself, what's became, I mean, is it rearrangement of the polymers, recharge of the polymers, or different explanations, what's the reason why films, why these structures so greatly change their behavior by means of these external factors. That's, let's say, our bridge to the mechanical part of the, hopefully, your experimental or your theoretical results, colleague. Yeah, that's all. That's all what I want to say. Questions, probably?
Have you got any questions? Once more. It was very interesting lecture. Thank you very much. Значит,
of the polymer.
Нет, не надо. Я ко всем обращаюсь, слушателям. Ну вот у нас тут небольшое ЧП произошло. Нам пришли и объявили, что здесь, значит, сотрудник заболел коронавирусом, и поэтому нас просят все.
Вас не слышно. Говорите, пожалуйста, в микрофон.
Так, а сейчас слышно?
Да, когда говорите в микрофон, слышно, а в остальное время, к сожалению, нет.
Светлана Михайловна, вас не слышно.
Так, вообще зал отключился. Уважаемые участники, единственное, что я знаю, да, что в Политехе на конференции один сотрудник заболел вирусом, и с завтрашнего дня конференция планируется в онлайн-формат. Что сейчас с секциями, что будет завтра, пока еще никто не знает. У меня у самой нет информации. Потому что как бы у нас еще в этой секции 2 доклада онлайн должны быть.
То есть тем, кто сидит и ждет доклада,
Я
оставаться
не знаю,
ждать.
понимаете, вот буквально это все выяснилось минут 10 назад, сейчас все переписываются, вот что знаю, все сказала. Как бы давайте пока посидим, я попытаюсь что-нибудь выяснить.
Хорошо, спасибо,
Потому что
Наталья,
зал
так и
почему-то
сделаем.
от нас отключился. Я не знаю, что у них случилось. Сейчас, пока не расходите из зума, я выясню и скажу. Ну, постараюсь.
Хорошо, договорились, спасибо.
Так, ждем информации. Надеюсь, что скоро будет.
Лекции 2 доклада онлайн.
Kostya, are you ready to begin?
Yeah, should I begin?
Yes, I think you can begin your lecture.
Okay. So,
Проблемы какие-то, да?
not yet. Can you see my slide?
Not yet. Oh, yes. Thank you. You begin your.
Yes, it's okay.
Can you see it?
Лекции 2 доклада онлайн.
Kostya, are you ready to begin?
Yeah, should I begin?
Yes, I think you can begin your lecture.
Okay. So
Проблемы какие-то, да?
not yet. And they come to the middle of the prairie, to the rails. The sun shines. No idea when the post train comes. No timetable of it. So, and they cannot hear anything. So then the chief of the band comes to the rail with his ear, and he says, "Okay, I guess the post train will come probably in 15 minutes." How can he realize this? So the sound propagation in the dense medium of the rail has much higher velocity as in the air. So he was able to hear a post train just several hours before as he will did it in the air. And to this story, to this aspect of the sound propagation in the media and the possibility to measure mechanical characteristics of the tissue through this physical principle, to this topic I will tell you today a little bit more in sense of the application in the medicine. So human vessels become stiffer with age in diseases of vascular origin, like arteriosclerosis, like arterial hypertension, and so on. And an interesting story here is that pathological structural vascular alterations occur primarily in small vessels in different organs and systems. Even so, they start there, and later the alterations can be seen in large vessels. So we will expect in the microcirculation earlier changes in the vasculature before it comes to the several hours before as he will did it in the air. And to this story, to this aspect of the sound propagation in the media and the possibility to measure mechanical characteristics of the tissue through this physical principle, to this topic I will tell you today a little bit more in sense of the application in the medicine. So human vessels become stiffer with age in diseases of vascular origin, like arteriosclerosis, like arterial hypertension, and so on. And an interesting story here is that pathological structural vascular alterations occur primarily in small vessels in different organs and systems. Even so, they start there, and later the alterations can be seen in large vessels. So we will expect in the microcirculation earlier changes in the investigate them using other imaging methods, but there is one of the not so much places in our body where we can see them almost undistorted directly optically. And a very interesting story about them is that one can see vascular abnormalities of the tissue through. So the most interesting story for us will be probably systemic diseases like arterial hypertension, like diabetes. You can see those abnormalities on the eye background, sometimes even in the early stages of the disease. And moreover, you can see the preclinical alterations of the microcirculation. And again, there is a direct link to cerebral microcirculation. So you can see preclinical alterations in the earlier stages of diseases of vascular origin. So the aim of the project, the results of which I want to present to you, is to provide in vivo automatic non-invasive examination of retinal vessel behavior, and on the base of this data to create an objective and quantitative to extract objective and quantitative information on age-related and pathological alterations in vascular. The interesting story about them is that one can see vascular abnormalities of the tissue through. So the most interesting story for us to diagnose the diseases of vascular origin. So again, as example, arterial hypertension or diabetes mellitus. So today I will tell you, so remember you about the assessment of arterial stiffness in microcirculation using the method of pulse wave velocity measurement. Then we'll switch to dynamic retinal vessel analyzer, and I will tell you how we developed a methodology to assess retinal pulse wave velocities in retinal arterioles. I will tell you about some results using this methodology, and in the end, we will speak about some perspectives on the application of these methods. So the human heart is beating and it pumps the blood through all our body, but together with this, this is a source of sound, and there is a sound wave which propagates through the whole arterial system of our body, or a so-called pulse wave which propagates through the vascular system. And the pulse wave velocity, the velocity of this propagation, is related to arterial stiffness. So in clinical practice of cardiologists, it's used to serve for several years, so more than 50, 60 years, as a blood pressure independent predictor of cardiovascular risk. So in dense, stiffer, diseased vessels, the pulse wave velocity, the velocity of this pulse wave propagation, is higher than in more elastic young vessels. So the higher the pulse wave velocity, the more stiff are the vessels from the clinical praxis. So how do they measure the pulse wave velocity in the macrocirculation in large vessels? So they use this is a somehow simplified explanation on that, but imagine you have a cuff to measure blood pressure, and you set it, for example, on the arm and forearm. So two cuffs proximal to the heart and another one distal to the heart, and you try to measure blood pressure simultaneously in both places. And if you can do it continuously, you will see that the blood pressure curve, so the temporal changes in the blood pressure over time, they are shifted. So the pulse wave comes first to the place which is proximal to the heart, and after that to the place which is more distal to the heart. So if we can measure the distance between the measurement places, and if we know the phase shift between the both curves, we can measure the pulse wave velocity as a distance divided by this temporal shift. So this is how do they do it, simplicity. And the question is, probably it is possible to measure a similar parameter in the microcirculation in small vessels. For example, in the eye, in the retinal vessels, I'll tell you about. The problem is you cannot set a pressure cuff on the eye, or you can do it, but how can you distinguish between the different places along a retinal artery to measure a phase shift and so on? So for these purposes, we use the methodology of retinal vessel analysis. The device retinal vessel analyzer produced by the German company Imedosystem allows for automatic non-invasive in vivo. This wave comes first, the diameter changes of retinal vessels. So actually we do here optical imaging. We do the imaging, the film, the movie of the retina, and we analyze every picture of 25 per second using the methods of medical imaging. So we digitalize the imaging and we analyze it mathematically. So in the end of the day, we have the information on vessel diameter changes of a chosen retinal vessel segment over time along the segment. So on the basis of these techniques, we can, for example, see how do the retinal vessel we have chosen pulsate over time. So we can see that the vessel diameter changes over time. Just a minute. And on the basis of this information, we created a method to measure a pulse wave propagation through retinal arteries. So similar to the methodology in the large vessels, we measure here simultaneously two segments, one which is proximal to the heart, one which is distal to the heart. But in this case, we are oriented to not to the pressure pulse, but to the volumetric pulse. So we are looking to the changes in the vessel diameter, but they are pretty related to each other. So we measure simultaneously the pulsations in two places along a chosen retinal artery. And after the pre-processing and the signal analysis, we see that two signals are shifted to each other. So we take this phase shift, we measure the distance between the place 1 and place 2, we calculate the relation to this of these two values, and then we'll receive a so-called retinal pulse wave velocity, which we believe is a measure of the arterial elasticity. The question is, so we have, because of the methodology, we can believe in this, but actually we need somehow to verify the methodology to say other people we are measuring something which is related to the stiffness of the vessels. One of the possibility is just to do it experimentally. Another possibility is to test it in clinical practice. So firstly, we tested the methodology in the clinical practice, analyzing signals of the patients and healthy people where we know that the arterial stiffness is different. So the true methodology is a little bit or much more complicated, and I don't want to go very far in the detail, but because of a so-called apparent pulse wave velocity, which is not the measurement of the arterial stiffness, we needed to filter not on the heart pulse rate, but at the 10th or higher multiple of the heart rate. Because of reflections in the vascular tree, these high frequencies are much better created for the analysis, and they give us the cue about the true pulse wave velocity and not about the apparent pulse wave velocity. We did here a cross correlation. We took several parts of the vessel segment and calculated the distances of several places along the chosen vessel segment through the reference part to the reference segment. And then we calculated the slope of the relation distance to the phase shift. We did it in two places along a vessel and each vessel of the examined people. And then we calculate at two places, one place which is a narrow place along the vessel, another place which was a wide place, and then we calculate the retinal pulse wave velocity as a mean of that pulse rate. But even because of different vessel diameters, we will have several values of pulse wave velocity. So therefore, we just try to somehow compensate for this information, because the story which was interesting, most interesting for us, was the stiffness of the vessel wall and not the vessel diameter, which we can measure directly. So we were able to show that the distances of several places along the chosen vessel segment through the reference part to the reference segment. And then we calculated the slope of the relation distance to the phase shift. We did it in 2 places along a vessel, and each vessel of the examined people. And then we calculate at 2 places, one place which is a narrow place along the vessel, another place which was a wide place, and then we calculate the regional pulse wave velocity as a mean of that pulse rate. But even because of different vessel diameters, we will have several values of pulse wave velocity. So therefore, we just try to somehow compensate for this information, because the story which was interesting, most interesting for us, was the stiffness of the vessel wall and not the vessel diameter, which we can measure directly. So we were able to show that the distances of several places along the result mildly hypertensive patients, so the people who were diagnosed with the diagnosis arterial hypertension, where we expected higher stiffness, stiffer vessels. 12 senior anamnestically healthy volunteers, so who believe they are healthy and did not take any medications, and 2 senior 63 years old aged healthy volunteers. So where we excluded risk factors. So we measured actually a large cohort of aged people, and only those who has a good cardiovascular profile were taken in this group. So what did we exclude in this group? So we took only the people with lower systolic and diastolic blood pressure, with not very high blood glucose level, without elevated cholesterol, and without extensive weight. These were our inclusion factors here. I formulated them as exclusion factors. So therefore, I hope I did not confuse you so much. So we excluded in this group the people with this criteria, with the characteristics. And as you can see here, we receive a sense of regional pulse wave velocities, the results actually we expected. Low pulse wave velocities in young anamnestic healthy volunteers. Higher, significantly higher pulse wave velocities in young hypertensives. A high variability as expected in the old anamnestic healthy volunteers who believe they are healthy. And you cannot imagine what did we receive in the group of validated old healthy volunteers. So probably something higher than in young anamnestic healthy. So the story is they were, in comparison to 2 groups in the middle, they were similar in their regional pulse wave velocities. Similarity means that their values were generally higher in comparison to young anamnestic healthy volunteers, but not really. So as we investigated these 2 groups in detail, we received the information on the alterations in this sense, but the alteration, the age dependence in the people who were validated healthy was not really high. So we are here in the area of 300-400 micrometers in second. I did not tell you what is this RU per second. This is a small remark on that. Generally, this is a micrometer, but because our eyes are not ideally spherical, there is a kind of correction on that. So in the reality, you measure it in some some arbitrary units, which are related to microns, a little bit more or a little bit less in several people. So we were able to show with this method that we can even see earlier alterations in the arterial hypertension. So for this purpose, we measured 68 young male subjects. So they were young, they were male people, just to exclude some confounders because of gender. And the people were healthy according to their main clinical parameters. body mass index, cholesterol, blood glucose, microalbuminuria. This is a biomarker that shows whether the microcirculation is okay. The vascular stiffness of large vessels were also okay, and even parameters, special parameters of retinal vessel analysis related to some other aspects are also within the norm. The only difference between these people were that we have a third of people with a normal and optimal blood pressure, and another third with the people with a so-called high normal blood pressure, so approximately 120 to 80, and hypertensive blood pressure people were. We were able to show with this method that we can even see earlier alterations in the arterial hypertension. So for this purpose, we measured 68 young male subjects. So they were young, they were male people, just to exclude some confounders because of gender. And the people were healthy according to their main clinical parameters. The normal optimal blood pressure group were shown a relative low retinal pulse wave velocities. The high normal blood pressure, as expected, showed us a high variability and was somewhere in the middle, and significantly different from both other groups. They were the hypertensive group. And again, several other clinical parameters which they use in clinical practice were not able to show that the groups are different, that the people are not healthy. So the method of retinal pulse wave velocity in retinal vessels shows age to 8 retinal arterial stiffness in healthy volunteers, elevated retinal arterial stiffness in aged volunteers with not excluded cardiovascular risk, and in patients with arterial hypertension, and microvascular alterations already in so-called preclinical stages of arterial hypertension, as you were able to see from my last slide. So in the perspective, we need to improve technically and validate in vivo our methodology. We need to do long-term alterations and repeatability studies. We need to check the high stability. We need to have a look to the selectivity in arterial hypertension, in arteriosclerosis, and in diabetes. So just to answer the question whether we can really distinguish these diseases on the base of this parameter retinal pulse wave velocity, or probably we can only repeat that the retinal pulse wave velocity is high in all these diseases. We need further longitudinal studies for early diagnostics, and we need to understand better the etiology of the parameter retinal pulse wave velocity, whether we can really distinguish the retinal pulse wave velocity in the constructed vessels from those in the calcified vessels, and so on. So we have a lot of homework, but we look to the story very optimistic. We have first results that are quite interesting. So in the end, I want to acknowledge my cooperation partners, and yeah, thank you for your attention.
Thank you for your report. Have you got any questions? I think later. Thank you once more. Mikhail Perelmuter is here.
Да, он здесь в зуме давно, но что-то не откликается.
Да-да, я здесь.
We are ready to listen to.
Слышно?
Да.
In the constructed vessels from those in the calcified vessels.
Can you see my screen?
Yes, it's okay.
My presentation is regarding analysis of bone density influence on stress near the dental implants. This presentation together with my colleague Elena Kasparov. At first, short contents of his presentation. At first, several words about statement of this problem, and several words about the method of analysis and the result of computations. At first, about dental implants. Dental implants with screw joints has two types. First type with a joint with screw, and second type joint with cement attachment. But in both cases, the screw, when we insert screw in the bone, make the big disruption on the bone, and after that, there a long period to bone healing, and the stability of implants strong depends of quality of bond. Quality of bond depends on bond density. From experimental view, bond density depends or proportional depends on module elasticity of bonds. In this case, we analyze the stress in bond, also in implants, the point of elastic modulus of bone, cortical and sponge bone. Some steps of solution. At first, we analyze the whole implant's structure with smoothed screw and surrounding bony tissue. Second step, analyze details of stress distribution in screw with screw details. Consider bone as isotropic and homogeneous material. From experiment observation, sponge bone varies in very wide scale, but practically sponge modulus about 0.1 to gigapascal, but we consider more depends or proportional depends on from 6 to 20 gigapascal. It's practically real modulus of cortical bone. At first stage, we calculate the full model, and also we consider only screw joint without the crown. Final terms, what we use, it's a well-known Abacus package, and boundary mod program, it's our program, and short several words about this boundary element program. We use direct boundary integral equation with Kernel solution for 2, 3, and axisymmetrical body, but now we consider only two-dimensional models for dental implants, and in boundary elements we use isoperiodic quadratic boundary elements. We may consider multi-material joints with several materials and different shapes and properties. First part of this calculation, we consider full model of implants. It's you can see it here. Can see it's compact bone, very thin layer. Most part of the bone is this sponge bone with nerve, with channel for nerves, and we applied zero displacement on out surface. It's with this layer, so the fixed displacement, and applied normal normal pressure on the crown. Here you can see boundary elements model for full dental implants and bone. Here are some results. With results obtained by bond elements, you can show maximal stress versus elastic modulus of spongy bone for plane strain, for compressive load at this case. If the elastic modulus of spongy bone increase, the maximal stress also increase and slightly decrease if the modulus is very big, but this zone for elastic modulus of spongy bone not met very often. It depends only on age of man. Practically, we work with first one-third part of this curves. Second graphs with maximal stress is spongy bone depends of modulus of compact bone. In this case, the stress decrease because in this case, if the modulus, you can show maximal stress versus elastic modulus of spongy bone for plane strain, for compressive load at this case. If the elastic modulus of spongy bone increase, the maximal stress also increase and slightly decrease if the modulus is very big, but this zone for elastic modulus of spongy bone not met very often. It depends only on age of man. Practically, we work with first one-third part of this curves. Second graphs with maximal stress is spongy bone depends of modulus of compact bone. In this case, the stress decrease because but the maximal stress variation approximately the same, but for rather small values of elastic modulus, the variation of this maximal stress not very big. Next step, we consider the stress analysis with taking into account the screw effects. Here, the model which take in account the symmetry of loading, because we consider the symmetry part of part of bone, and here the implants with 12 screw and thin layer of compact bone and sponge bone. In this case, the dependence of maximal stress on modulus of sponge bone slightly different of previous case, and also its decrease for rather big values of modulus of sponge bone. Why it's happened? Because in this case we have a rather big stress concentration in this screw joint. In this case, for big modulus of this bone, the stress concentration move from along with this position, and maximal values slightly decrease if with the modulus increase. Here we may see distribution of intensity of stress along the half of this model. This intensity of stress along the sponge bone and distribution along the dental implants. Elastic the stress inside the sponge bond rather reasonable because the strength of limit strength of a sponge bond about 15 megapascal, and this value more or less reasonable for dental implantation. Next part, we consider the similar graphs for maximal stress in compact bond and the sponge bond, and compare two methods. Results obtained in two methods, by finite elements and bonded elements. It's also confirmation the correctness of our results. The results obtained by two different methods very, very close. Here you may see the lines of equivalent stress for two different properties of bond. Sponge bond 0.5 and compact 18 gigapascal, and sponge extremely big for close, the more same compact bonds elastic modulus. In this case, in last case, we can see more or less uniform distribution stress along joint between the implants and bone. In this case, the most stress concentration observed on the neck of implants, and this very dangerous case, because in this case may start the destruction of bone, resorption of bone, and after that the implant must be excluded. And last part of analysis with analysis the maximum stress in for full models. In this case, we consider full models with sponge bone, compact bone, and apply to inclined loads to the top of the dental implants on this place. In this case, we have a more or less the same dependence, but the value of maximum stress slightly more when we consider the symmetrical model. Here we may see the distribution the indices of stress along the boundary implants and sponge bone. And some conclusion from this calculation. We obtain dependence maximum current stress on elastic moduli of bone, and obtained for interaction full implants with smooth screw, and analyzed the same dependence taking in account stress concentration. Increasing the elasticity modulus on sponge bone increases the load transfer to this bone, wherefore equivalent stress in sponge bone increase. Stress in cortical bone tissue with increase of modulus sponge bone reduced due to the reduction of load transfer to this bone. Stress in sponge bone decrease with increasing elasticity of cortical bone. Why this analysis, most in this question, why this analysis need to dental doctors? Because the effectiveness of the dental implantation depends on strength of bone, in fact, on density of bone. If density of bone rather reasonable on reasonable level, the dental implantation may be effective. To analyze the density of bone, there are some experimental methods, but to compare the experimental with some calculation need some results about stress, and how the stress depends on bone density. That's all. Thank you for your attention.
Thank you for your